Welcome, and greetings to Science and Sleep, a place where deep curiosity transforms into a soothing bedtime story, and the wonders of science unwind at the speed of a gentle breath. This evening, we will drift into the most profound question of scale that mankind can possibly ponder. Just how incredibly massive is the cosmic ocean compared to the galactic oasis we call our home? It is a mystery with an overwhelming magnitude baked right into its core. Even so, no matter how many calculations or dimensions we are given, it always leaves our human imagination completely overflowing. We reside within a structure that is unimaginably colossal, yet we simultaneously look outward into an environment that is grander still. Tonight, my goal is to guide you slowly through that monumental contrast. Before we begin our journey into the night, I would love to discover what corner of our world you are tuning in from tonight. Perhaps you are resting in a bustling metropolis where the cosmic lights are completely drowned out. Or maybe you are out in the countryside where the Milky Way itself can be observed cutting a brilliant path across the open sky. It might be the middle of the night and you are completely tucked into bed. Or perhaps it is just a quiet afternoon and you are simply searching for a moment of calm reflection. Whichever it is, you and I are sharing this exact instance together, and that is a beautiful little miracle all on its own. If you find this type of peaceful exploration comforting or helpful, it would mean a lot if you could hit the like button or subscribe. That way, other souls who need a soothing voice to drift away with can find this sanctuary as well. For now, take a deep breath, settle comfortably into your seat or your pillow, and let us contemplate what it truly means to be tiny in a cosmos that demands to be absolutely endless. It helps to briefly visualize yourself standing outdoors. Picture a night that is crisp and clear, the atmosphere completely still, and an open sky stretching above you, peppered with stars. Maybe you can only spot a handful of them due to the glare of nearby streetlights, or perhaps you can see thousands. Every single one of them is a glowing sun from another system, many surrounded by orbiting worlds, and all of them bound to something much grander. When you look up at the heavens, you are not merely viewing random points of light scattered blindly across the dark. You are witnessing a piece of a colossal architecture, a spiral galaxy known as the Milky Way that holds all these suns together in a graceful, definitive structure. It spans such an immense distance across the void that even if you could travel at the absolute speed of light, you would still need tens of thousands of years just to cross from one edge to the other. Yet despite this unbelievable vastness, our entire galaxy is merely a single specimen among billions, or perhaps even trillions, existing throughout the cosmos. It is quite simple to throw around these massive numbers, but what does it actually feel like to weigh them against each other? Tonight, we are going to take that measurement one quiet step at a time, keeping in mind that while these concepts sound gigantic, they are merely signposts pointing toward a reality our minds can barely begin to grasp. When you stand out beneath the starlight, it is incredibly easy to view yourself as completely insignificant, as if the great universe is unfolding endlessly in every single direction while you are just a microscopic dot on top of another dot, dissolving into the background. However, there is a completely different way to look at this. You are an intrinsic piece of the galaxy, and you are a piece of the universe, the very same atoms that were forged deep inside burning stars billions of years ago are alive right now inside your own body. The vast space above you is not disconnected from you. It is completely continuous with the very room where you are currently resting. The ground beneath your feet, the oxygen filling your lungs, and the warmth of your skin are all deeply intertwined with the exact same cosmos we are about to measure. So, rather than feeling small, you can choose to feel entirely included, beautifully woven, right into the grand scale of everything we are describing. As you let that comforting thought settle in, reflect on how extraordinary it is that we can even pose a question like this in the first place. For the vast majority of human history, the universe was simply seen as a fixed dome in the sky, and humanity did not even know that a galaxy existed as an actual structure. Our ancestors looked upward and saw individual stars, or occasionally a pale band of light cutting through the heavens. but the realization that all those stars were actually bound together into one massive spinning disk, and that this disk itself was just a tiny fragment of a much grander reality, is a very modern discovery. Just a single century ago, top astronomers were still actively debating whether other galaxies even existed at all, or if every single thing we could observe was locked inside the boundaries of the Milky Way. Today, we understand that the Milky Way is merely a lone island, floating among countless others in a vast cosmic ocean. In that incredibly brief window of time, our collective perception of size has expanded by a factor that defies simple words. That beautiful expansion of human awareness is exactly what we are going to explore together. Think for a moment about how you perceive distance in your everyday life. It is just a few steps to wander into the kitchen, a quick walk around your neighborhood block, a drive over to a neighboring city, or a long flight across an entire ocean. Every single one of those distances feels real and tangible to you. You know exactly what it feels like to spend an hour sitting in a car, and you know the exhaustion of a long-haul flight. But the moment we begin to compare galaxies to the entire universe, the parameters grow so far beyond human comprehension that everyday words like miles or kilometers lose all their meaning. Instead, scientists must rely on light years, which represents the total distance that light can travel over the course of one full year. Light, which is the absolute fastest entity in existence, covers nearly 10 trillion kilometers in a 12-month period. Yet even this staggering cosmic yardstick struggles to keep up with the scale of what we are analyzing. Our own galaxy spans roughly 100,000 light-years from side to side. That alone is a number that completely resists mental visualization. But when you compare it to the entire universe, which stretches across more than 90 billion light-years in observable terms, our galaxy is transformed into a single step on an infinite staircase that seems to climb forever. This is precisely where our imagination must step in. Tonight, we will take things very slowly, allowing every single number to breathe and letting every comparison unfold without any rush, so that instead of drowning in a sea of data, you can comfortably construct a mental landscape. You can orient yourself within the galaxy, see its incredible width, compare it to the neighboring clusters of galaxies around us, and finally weigh it against the observable universe itself. By the time we finish, you will not possess a flawless mental picture, as that is simply impossible, but you will gain a profound sense, a peaceful awareness of the true relationship between our cosmic home and the grand universe surrounding it. That is all we need for this evening, because capturing even a tiny hint of this scale is more than enough to leave the mind completely humbled and deeply soothed. Take another gentle, slow breath and hold on to that mental image of resting beneath the stars. Notice how they gently flicker and how some shine much brighter than others. What your eyes are processing is just a microscopic fraction of what is truly out there. In reality, from most locations on our planet, only a few thousand stars can actually be seen with the unprotected human eye. Yet our galaxy acts as a home to hundreds of billions of stars, the vast majority of them completely cloaked from our vision. Try to imagine multiplying the night sky you see above you by a factor of 100 million. That gets you much closer to what the Milky Way actually contains. Now imagine that this entire unimaginable collection of suns, gas clouds, stellar dust, and invisible dark matter is just a single galaxy floating among an infinity of others. It is the ultimate contrast between a single grain of sand and an entire beach, or a lone page compared to a grand library. The metrics become so incredibly vast that they almost start to sound comical. Yet here we are, resting comfortably and asking these questions, letting our minds drift across these massive scales without any pressure to solve them, but simply wanting to feel them. It is worth pausing right here to reflect on why contemplating this vastness feels so deeply soothing to us. Normally, when we are confronted with something that is impossibly large, our natural instinct is to feel completely overwhelmed. However, when it comes to the cosmos, the exact opposite frequently takes place. Thinking deeply about the galaxy and the universe can be strangely comforting, because it immediately puts our everyday anxieties into true perspective. The pressure of a stressful daily task, or the anxiety of a single passing moment, suddenly seems to shrink to nothing when framed against a backdrop of billions of suns and trillions of galaxies. This does not mean that your personal concerns do not matter. They matter immensely, but they are nested inside a much larger framework, and that realization can create a beautiful sense of internal balance. You are certainly not the center of the cosmos, but you are an active part of a reality that encompasses absolutely everything in existence. In a beautiful way, it serves as a reminder that there is ample room for you, both literally and figuratively, within the grand architecture of life. Now, let your thoughts drift back down to the solid Earth beneath you. This planet is our launch pad, and from here we will take off using our imagination, rising first into our home galaxy and then venturing far beyond. The Earth measures roughly 12,700 kilometers across, which is a dimension our minds can grasp with relative ease. Spend a few hours sitting on a plane and you have crossed an entire continent. Spend a single day in orbit and you have completely circled the globe. But when you scale this up to our solar system, where the planet Neptune orbits at a distance of nearly 5 billion kilometers away, the Earth instantly feels incredibly small. Next, place that entire solar system inside the Milky Way, which spans across 100,000 light years, and our planetary system is reduced to a microscopic dot, too small to ever be noticed. Finally, compare the Milky Way to the universe, which reaches across at least 93 billion light years, and our entire galaxy becomes a mere dot in turn. This magnificent cascade of scales is precisely what makes the comparison so completely awe-inspiring. Every single step is an entire world of its own, yet every step shrinks to insignificance the moment you move to the level above it. And this is merely the introductory chapter. For the time being, we are still standing right here under that starry sky together, just starting to decipher how all these puzzle pieces fit into place. The night is beautifully calm, the air is perfectly quiet, and the underlying thought is simple. The galaxy is vast, but the universe is grander still. When we think about the place we inhabit, our minds usually stop at the borders of the Earth, sometimes reaching out a bit further to the moon or the sun. Beyond that, things start to feel highly abstract, as if they belong to a completely separate category of existence. But the reality is that our genuine home, the actual structure that shelters every single star we see at night and every planet we have ever dreamed up, is the galaxy itself. The Milky Way is not some far-off cosmic object completely separate from us. It is the physical house we are already living inside. To talk about our galaxy is to speak about the grand stage upon which every single piece of our solar system exists. Learning about it, even in a small way, is like understanding the layout and shape of the entire house you live in, rather than spending your life only describing a single room. Tonight, let us take all the time we need to look around inside this cosmic home, noting its unique features and true dimensions, anchoring ourselves within it in a way that feels grounding and peaceful. If you could step back incredibly far from the Earth, rising high above the blur of our atmosphere, and travelling past the orbits of all the planets, you would eventually witness the true form of the Milky Way revealed in all its glory. From our current vantage point on the surface of the Earth, we only ever catch passing glimpses of its real geometry. That cloudy, hazy band of light that weaves across the night sky on dark, clear evenings is actually our edge-on view, looking directly through the disk of the galaxy. But if you were viewing it from the outside, the Milky Way would reveal itself as a spectacular spiral galaxy, a flattened disk featuring elegant arms that sweep gracefully outward, decorated with stars, cosmic nebulae, and stellar clusters. Right at the very centre sits a highly dense galactic bulge, a tightly packed sphere of ancient stars, all orbiting a supermassive black hole known to science as Sagittarius, a star. This entire cosmic structure is woven together with interstellar dust and gas, glowing softly in wavelengths of light that our human eyes cannot naturally perceive. Putting it into simple words is easy enough, but trying to imagine standing outside of it and looking back is a far greater challenge for the mind. Even if we cannot perfectly visualize it, we can still place ourselves within its grand outline and start to appreciate our exact location. The main disk of the Milky Way measures about 100,000 light-years from side to side and is roughly 1,000 light-years thick. Within this colossal disk, stars orbit around the centre like a giant, slow-moving whirlpool. Our own solar system is not located in the heavily congested centre. Instead, we reside out on one of the secondary spiral arms, known as the Orion Arm, or the Orion Spur, situated roughly 27,000 light-years away from the core. That specific distance alone is incredibly difficult to truly comprehend. Light travelling at the absolute maximum speed limit of the cosmos still requires 27,000 years just to make the journey from the galactic centre to our eyes. This means that when astronomers peer at the central hub of our galaxy, they are not viewing it as it exists in the present moment. They are seeing light that left those stars long before human civilization had even begun. We live inside a galaxy that carries its own ancient history, simply due to the way light travels across it. It is well worth pausing right here to contemplate what it truly means to live inside this kind of cosmic disk. The layout of the night sky we see is not a random arrangement. It is the unique perspective from our specific neighbourhood in the galaxy. When you look directly toward the dense, thick band of the Milky Way, you are looking straight into the core plane of the disk, where billions of stars are tightly crowded together. Conversely, when you look away from that band, the sky appears much thinner because you are looking out of the flat disk and into the sparse stellar halo that surrounds our galaxy. Every single direction you look is still inside the galaxy, but the overall density changes completely based on your line of sight. In a way, every single person stargazing from Earth is exactly like someone standing deep inside a vast forest. If you look straight along the path of the trees, the trunks appear tightly packed and endless. But if you look directly upward, wide gaps of open sky appear through the canopy. The forest remains the same, but your perspective alters it entirely. Our galaxy functions in the exact same manner, only the trees are giant suns and the forest stretches out for tens of thousands of light years. Inside this grand home, there are landmarks that are just as distinct as the mountains or oceans found on Earth. There are globular clusters, which are tightly bound knots containing hundreds of thousands of ancient stars that orbit the galaxy like miniature satellites. There are colossal nebulae, magnificent clouds of interstellar gas, and dust where brand new stars are actively being born, lit up from the inside by glowing hydrogen. There are supernova remnants, the expanding shells of exploded stars scattered across space like ancient cosmic fossils. And threading through absolutely everything are the spiral arms themselves, regions where stars and raw gas are more tightly packed together, winding around the galactic core in beautiful arcs. Our solar system travels right along with the rest of the disk, completing a single loop around the galactic centre once every 230 million years. To put that in perspective, in the entire span of time since the dinosaurs walked the Earth, our solar system has completed just one single orbit of our galaxy. Every loop is unimaginably long on human timelines. Yet the galaxy itself has been around for more than 13 billion years, meaning it has completed dozens of these full rotations since its birth. We reside in a place that is not only monumentally vast in terms of space, but incredibly ancient in terms of time. The supermassive black hole resting at the dead centre, Sagittarius A star, deserves its own special mention. It packs roughly 4 million times the total mass of our Sun, compressed down into a region of space no larger than the orbit of the planet Mercury. It is completely invisible to our eyes, but its massive gravitational signature dictates the wild orbits of the stars closest to the core. For decades, astronomers painstakingly monitored the movements of those central stars and proved that only a black hole of such immense mass could possibly explain their extreme speeds. In the year 2022, the International Event Horizon Telescope collaboration unveiled the very first direct image of the region immediately surrounding Sagittarius A star, showcasing a blazing ring of superheated gas swirling around a dark shadow. That central shadow is the closest humanity can ever come to genuinely seeing a black hole. Knowing that such a massive monster resides at the heart of our galaxy can feel a bit unsettling, but it is also deeply awe-inspiring. In a strange way, It makes the galaxy feel like a complete living system, with a powerful heart beating hidden away in its core. Enveloping the flat disk and the central bulge is another major component known as the halo. This is a massive, roughly spherical zone that reaches out far beyond the visible borders of the disk, holding scattered stars and ancient globular clusters. Much more importantly, it is believed to host immense quantities of dark matter, an invisible form of mass that does not emit any light but exerts a powerful gravitational pull. Without the presence of this dark matter, the stars travelling in the outer edges of the disk would not orbit the way they do. The galaxy would simply fly apart into the void. Instead, this unseen matter serves as the invisible glue holding the entire structure together. In this sense, the Milky Way is defined not only by what we can see, but by what remains completely invisible to us. A gentle reminder that our picture of home is still wonderfully incomplete. Up to this point, we have been speaking in massive terms of light years and hundreds of billions of suns. Let us slow down our pace and anchor those grand numbers a little bit more. Our sun is merely a single star among roughly 200 to 400 billion stars existing within the Milky Way. That estimated range is quite broad, because it is highly difficult to accurately count stars that are heavily obscured by interstellar dust, or have grown incredibly faint with age, but even the lower end of that estimate is staggering. 200 billion suns, each potentially hosting its own family of planets. If even a tiny fraction of those stars shelter worlds capable of supporting life, the total number of habitable environments in our galaxy alone is absolutely enormous. Yet, despite this incredible abundance, stars are separated by such massive distances that the closest one to our own system, Proxima Centauri, is still more than 4 light-years away. Even if our galaxy is completely teeming with life, the gaps between systems are so immense that meeting our neighbours would be an extraordinary challenge. The Milky Way is simultaneously crowded and profoundly lonely. It is a brilliant city of lights, but with streets so incredibly wide that every individual household feels completely isolated from the rest. As you let that poetic concept unfold in your mind, think once more about standing outside beneath the night sky. When you look up at that hazy band of the Milky Way, your eyes are tracing the side of the cosmic disk, your gaze travelling through thousands of light years of stars. That incredible view is only possible because we are looking at it from the inside. If you were standing on the outside, you would see the entire glorious disk stretched out across space, tilted slightly, glowing softly in the dark. Astronomers obviously cannot leave our galaxy to take a real picture of it from the outside. Instead, by closely analysing other spiral galaxies out in the cosmos, they can infer exactly what our own home must look like. In a beautiful way, every photograph we capture of another spiral galaxy acts as a cosmic mirror held up to us, showing us what our home looks like if we could only step outside its front door. Those breathtaking images taken by space telescopes reveal elegant structures, spiral arms lined with hot blue stars, lanes of dust winding like dark smoke, and glowing regions celebrating the birth of new suns. They are undeniably beautiful, but their greatest gift to humanity is that they allow us to visualize the true shape of the place where we live. This is not just idle daydreaming. Grasping the true dimensions and architecture of the Milky Way is absolutely essential if we want to accurately place it in the context of the grand universe beyond. Only by carefully measuring our home can we begin to compare it to the scale of the wider cosmos. Over the years, astronomers have utilized a brilliant mix of methods to chart the galaxy. They monitor the precise velocities of stars, map out the distribution of hydrogen gas, and use advanced radio telescopes to look straight through thick walls of cosmic dust. The ongoing Gaia mission, launched by the European Space Agency, has mapped the exact locations and movements of more than 1 billion stars, providing us with a 3-dimensional map of the Milky Way in unprecedented detail. With every new piece of data gathered, our image of home becomes a little bit sharper. Yet the sheer vastness of the galaxy ensures that grand mysteries will always remain. Even now, the outermost borders of the disk and the halo are only faintly understood. The more we discover, the more remarkable it becomes that you and I are here at all. Our solar system floats quietly along its orbit in the Orion Arm, positioned far enough from the chaotic center to avoid the cosmic hazards of hyperdense star clusters, yet close enough to enjoy the incredible richness of the galactic disk. It is a perfect cosmic address that provides long-term stability, steady sunlight, and a magnificent view of the night sky that inspires the exact questions we are asking tonight. Living inside a galaxy is not an unusual phenomenon. Every star in the universe belongs to one. But possessing the ability to describe it in detail, to measure its true scale, and to compare it to the boundless universe beyond is a beautiful gift of both science and imagination. As this thought continues to unfold, notice how the massive scale of the galaxy starts to feel a bit more comfortable and familiar to you. At first, a number like 100,000 light-years sounds completely overwhelming. But once you place our solar system within it, once you picture the sweeping arms, the central bulge, the protective halo, and the supermassive black hole anchoring the core, it all starts to take shape exactly like a familiar map of a city. You know precisely where you are situated in relation to the center. You can visualize the direction of the spiral arms. You understand that the entire disk is spinning slowly through space, carrying absolutely everything along with it. You realize that the night sky is simply your local neighborhood viewed from the inside out. Equipped with that grounding knowledge, your mind can confidently begin to ask the grander question: if this is the scale of our galaxy, how much larger is the boundless universe that waits beyond it? But before we take that giant leap outward into the deep void, let us choose to linger right here a little longer in the vast night of our galactic home, allowing its beautiful shape and ancient age to truly sink in. The Milky Way is not a distant background drop. It is the physical place where we experience every single moment of our lives. Its gravity keeps us anchored, its stars provide us with light, and its graceful arms give structure to our night sky. To truly appreciate its scale is to feel deeply humbled, yet wonderfully sheltered. This is our sanctuary in the vast cosmic night. Knowing that truth makes our next step outward into the universe even more meaningful. When we discuss the Milky Way, it is all too simple to fall into the routine of labeling it as our galaxy, without taking a quiet moment to consider what that term genuinely implies. Galaxy is one of those words that feels entirely common. It is a word you might initially hear as a young child when an elder gestures toward the heavens and explains that all the stars belong to the exact same massive family. Still, if someone were to pull you aside and ask you point blank, what exactly is a galaxy? The answer is far less straightforward than it appears on the surface. It is a term that encompasses something both elementary and incredibly deep, an entity that can be categorized by the laws of physics, but can only be truly grasped by stepping back to visualize how space behaves on the grandest scales of existence. This evening, let us take all the time we need to break down that concept, not with the hurried pace of an academic textbook definition, but with the slow, steady rhythm of a peaceful conversation where each layer is gently laid on top of the last. By the end of our talk, the word galaxy will feel clear, grounded, and no longer like a distant, cold abstraction. The most natural place to start our exploration is with the stars. At its most visible level, a galaxy is a colossal gathering of suns bound tightly together by the unyielding pull of gravity. It holds hundreds of billions of them in the specific case of our Milky Way. There are far fewer in the case of miniature dwarf galaxies, and substantially more inside the true giants of the cosmos. These suns are not tossed blindly or randomly through the void of space. Instead, they are organized into beautiful patterns, disks, and protective halos that endure for billions of years. The invisible cement that keeps them united is gravity, constantly drawing every single star toward every other one, while their collective orbital momentum keeps the entire system stable and balanced. Without gravity, stars would simply wander away, scattered across the dark universe like escaping sparks in a heavy wind. But because gravity is ever present, they remain bound to one another, perpetually circling a shared center and orbiting like planets around a central sun, only on a monumentally grander scale. Yet stars alone do not tell the complete story of a galaxy. These cosmic islands also house immense reservoirs of gas and dust, which serve as the raw material from which brand new suns are born. These interstellar clouds are frequently spread incredibly thin across vast domains, completely invisible to the unprotected human eye but glowing brightly when viewed through radio and infrared instrumentation. Deep within their cores, under the perfect circumstances, gravity pulls matter together, compressing it tightly until nuclear fusion ignites and a brand new star begins to shine. Galaxies, therefore, are not static museums of stars. They are active factories where suns are perpetually manufactured and destroyed, and where the eternal cycle of birth and death unfolds across eons of time. A single galaxy can simultaneously host regions where infant stars are bursting into existence in tight clusters, glowing intensely hot and blue, right alongside quiet sectors where ancient dying stars are slowly fading into dim red embers. It is an integrated system that holds both youth and extreme age, vigor and steady decline, all at the exact same time. There is yet another crucial ingredient that makes a galaxy what it is, one that is completely hidden from our sight, but is no less vital to the structure. That mysterious ingredient is dark matter. When astronomers measure the precise speeds at which galaxies spin, they encounter a major puzzle. The stars travelling along the outermost borders are moving far faster than they should be, behaving as if they are being held in place by an omnipotent, invisible hand. The only viable way to explain this phenomenon is to deduce that galaxies contain vastly more mass than what our instruments can actually see. This hidden mass does not emit, reflect, or absorb any light whatsoever, but it exerts a powerful gravitational force that dictates the motion of visible stars and gas clouds. By current scientific consensus, the vast majority of a galaxy's total mass is comprised of dark matter. Without its presence, galaxies as we understand them simply could not exist in our universe. Therefore, when we use the word galaxy, we are describing an intricate structure made of stars, gas, and dust, but one that is also nestled inside a colossal, invisible envelope of matter that completely outweighs everything we can see. Galaxies also frequently house distinct central anchors, typically in the form of supermassive black holes. These gravitational titans, which can be millions or even billions of times the mass of our Sun, sit quietly at the core of galaxies, their extreme pull shaping the orbits of the stars nearest to the centre. Some of these central monsters are highly active, aggressively feeding on surrounding gas and dust while blasting out titanic jets of raw energy that can be seen across the universe. Others, much like the one resting at the centre of the Milky Way, are relatively peaceful and quiet, only occasionally flaring up in brightness when a wandering star or a rogue cloud drifts a bit too close to the edge. The universal presence of these black holes strongly implies that galaxies and their central monsters grow up together, each profoundly shaping the development of the other over cosmic time. To try to define a galaxy without acknowledging its core would be like leaving out the very heart of the entire system. Up to this point, we have simply catalogued the individual components: stars, gas, dust, dark matter, and supermassive black holes. But a galaxy is far more than a simple checklist of parts. It is also fundamentally defined by its overall structure. Galaxies manifest in distinct geometries that astronomers categorize into clear groups. There are spirals featuring elegant sweeping arms, ellipticals that appear much more rounded, smooth, and aged, and irregulars that possess no definitive shape or symmetry. The Milky Way is classified as a barred spiral, meaning that a long linear bar of stars cuts straight through its centre, with the magnificent spiral arms extending outward from the tips of this bar. While these broad classifications help us organise the cosmos, the reality is that every single galaxy is entirely unique, uniquely shaped by its own personal history of growth, environmental influences, and cosmic collisions. Galaxies merge with one another, crash into each other and tear each other apart over billions of years, only to eventually settle down into entirely new forms. They are not isolated, static sanctuaries. They are evolving systems constantly being moulded by both their internal physics and the grand universe surrounding them. To deepen our understanding of what a galaxy is highly useful to examine what it is not. A galaxy is not merely a temporary cluster of stars casually drifting through the same general region of space. It is not a brief accidental alignment of celestial bodies that happen to be close to one another at a single point in time. It is an intensely bound gravitational system, a true family of stars and cosmic matter whose physical connections are strong enough to endure for billions of years. Furthermore, a galaxy is not a visual illusion like a constellation drawn in the sky from our specific viewpoint on Earth. The familiar shapes of constellations are entirely accidental patterns. The stars that form them only appear close together from our perspective, while in reality, they are separated by massive gulfs of depth. A galaxy, by contrast, is an undeniable physical structure, a genuine island in the universe that holds itself together through its own internal forces. We can also choose to define a galaxy by its incredible range of scale. At the absolute smallest end of the spectrum are dwarf galaxies, which can hold as few as 100 million stars. While these structures are still completely massive by human standards, they are microscopic compared to the giants. At the absolute largest end of the scale are titanic galaxies that boast trillions of stars and reach across hundreds of thousands of light years. Sitting comfortably in the middle of this range are galaxies like our own, mid-sized spirals housing a few 100 billion suns. Every single tier has its own cosmic role to play. Dwarf galaxies frequently serve as satellites to larger systems, orbiting around them for eons and occasionally being consumed by them. Giant galaxies dominate the centers of massive clusters, their extreme gravity pulling in smaller companions to fuel their ongoing growth. The spectrum of size is truly vast, but the underlying definition remains firm. A galaxy is a cohesive system large enough and bound tightly enough to be entirely self-sustaining over billions of years. The question of what exactly constitutes a galaxy has not always been so crystal clear to humanity. Just a single century ago, top scientists were locked in a fierce debate over whether the spiral shapes observed through powerful telescopes were simply small gas clouds located inside the Milky Way, or separate independent island universes existing far beyond our borders. The definitive answer finally arrived in the 1920s, when Edwin Hubble carefully calculated the true distances to these mysterious spirals, proving once and for all that they resided far outside our galaxy and were massive systems in their own right. That single realization instantly expanded the true scale of the universe by an unbelievable margin. All of a sudden, the Milky Way was no longer synonymous with the cosmos. It was suddenly reduced to a single specimen among a vast sea of galaxies. Since that historic moment, our collective understanding has exploded. With advanced modern space telescopes, we can now observe billions of galaxies, each one a magnificent, self-contained system. The word galaxy has transformed into a fundamental unit of cosmic architecture, as foundational to our understanding of space as the word star or planet, but operating on the grandest imaginable scale. When you hold that word in your mind tonight, let it feel less like dry scientific jargon and more like a real description of a place. A galaxy is a sanctuary for billions of suns, a cradle for new light to emerge, and a deep well of history stretching back almost to the very beginning of the universe. It represents a perfect cosmic balance between gravity and momentum, between visible stars and invisible matter, and between organized structure and chaotic dynamics. It is not merely a pretty object to peer at through a telescope, but the actual physical environment in which every single star we have ever known spends its entire life. In fact, when we describe the universe on its grandest scales, we are essentially describing a vast collection of galaxies. In that sense, galaxies are the fundamental bricks of the cosmic wall, the core units from which the entire universe is constructed. Think once more about the Milky Way, not as a completely unique entity, but as a classic example of this definition. It is a barred spiral holding hundreds of billions of suns, enveloped by a massive dark matter halo and containing gas, dust, and a supermassive black hole at its core. That technical description is enough to classify it as a textbook galaxy. But then, let your mind picture Andromeda, our closest large neighbour in the dark. It is another magnificent spiral, even grander than the Milky Way, featuring its own central anchor, its own sweeping arms, and its own billions of suns. Now, visualize the dwarf galaxies like the Magellanic Clouds, smaller, irregular companions that orbit around us like loyal satellites. Every single one of them is a galaxy too, because they all adhere to the exact same physical pattern. They are bound systems of stars and matter that remain entirely stable over cosmic time. If you were to cast your gaze outward from our galactic borders, you would see these structures scattered through the void, sometimes floating completely alone, and sometimes gathered in close groups. These smaller families combine to form massive clusters, which then link together to form even grander structures. But through all those escalating layers, the fundamental building block remains the galaxy. In that sense, to ask what a galaxy is to inquire about the core building blocks of the visible universe. Without the existence of galaxies, there would still be stars, but they would be scattered blindly through the void, never organized into enduring systems. Without galaxies, our night sky would display no beautiful bands of light or structured patterns, but only random, isolated sparks. With galaxies, the cosmos takes on a beautiful architecture, patterns that can be carefully mapped, measured, and understood by human minds. Now, let your thoughts drift back down to that single, elegant word, galaxy. It is incredibly easy to let it roll off the tongue without giving it a second thought. But buried inside that word is a richness of meaning that deserves time to fully unfold. It is a word that signifies a home for billions of suns and the eternal cycles of stellar creation and destruction. It represents hidden halos of dark matter, completely unseen but absolutely essential to existence. It speaks to a deep history of violent collisions and mergers, with ancient scars written directly into the modern orbits of its stars. It carries a beautiful diversity of form, ranging from perfect spirals to smooth ellipticals and chaotic irregulars, and it represents an absolute scale of distance that stretches across tens or hundreds of thousands of light years. To define this word is not to shrink its majesty, but to fully appreciate just how much weight it carries. In the quiet comfort of this evening, with the stars still imagined overhead, you can let that definition gently settle in. A galaxy is not something far away or detached from you. It is the grand structure you are living inside this very second. To know what it is to understand exactly where we are, and once that core foundation is firmly in place, once the meaning of the word transforms from a mystery into a description of home, we can confidently move outward once again. When you picture the Milky Way, it is highly tempting to only visualize that hazy band of light cutting across the night sky, the faint milky glow that originally inspired our ancestors to give the galaxy its name. That view is undeniably beautiful, but it is also deeply deceptive because from our fixed position inside the disk, we can never view the true outline of our galaxy. It is exactly like trying to comprehend the complete geometry of a forest while standing right in the middle of the trees. The trunks immediately surrounding you give you a clear sense of local density, but only by rising high above the canopy could you view the full pattern of the woods. For centuries, astronomers faced this exact same obstacle with the Milky Way. They could easily see that stars were concentrated in a broad, flat plane, but it is only within the last century that we have truly begun to decipher the complete shape and dimension of our galactic home. Tonight, we are going to let that map unfold carefully in our minds, so that the galaxy transforms from a vague glowing ribbon into a clear landscape we can hold in our thoughts. The Milky Way is what scientists classify as a barred spiral galaxy. This structural designation means it is shaped precisely like a flat disk, featuring long, elegant arms that curl gracefully outward from a prominent central bar of stars. If you could rise high above it in your imagination, you would observe a brilliant core, a thin, elongated, bar-like structure of stars, and then sweeping arms that spiral around the center like ribbons in the wind. the entire disk is remarkably flat, spanning roughly 100,000 light-years from edge to edge, but measuring only about 1,000 light-years thick. In relative terms, that thickness is almost nothing compared to its width, resembling a single thin sheet of paper stretched out to an unimaginable size. This extreme thinness is precisely why the galaxy manifests as a narrow, concentrated band in our night sky. From our position inside, when we look straight across the disk, our eyes are processing layer upon layer of stars packed tightly together. But when we look perpendicular to that disk, we encounter far fewer stars and a vast amount of empty space. Right at the dead center of the Milky Way lies the bulge, a rounded, spherical hub packed with older generations of stars, dense clouds of interstellar gas, and the supermassive black hole known as Sagittarius A star. The bulge is not a perfect sphere. It is slightly elongated, creating the appearance of a distinct bar when viewed from specific angles. This stellar bar is a hallmark feature of the Milky Way's architecture, extending for roughly 27,000 light-years across the central core. From the outer tips of this structural bar, the great spiral arms emerge, winding outward with a smooth, graceful curve. These arms are not solid, rigid structures like the blades of a fan. Rather, they are moving regions of higher density where gas clouds and stars are naturally more concentrated. As individual stars complete their orbits around the galaxy, they smoothly pass in and out of these dense arms, creating the visual impression of continuous structures, even though the specific stars occupying them are constantly changing. Mapping these arms precisely is an extraordinary challenge because of our position locked inside the disk. Even so, astronomers have successfully identified several main spiral arms in the Milky Way. These major structures include the Perseus arm, the Scutum Centaurus arm, and the Sagittarius arm. Our own solar system resides in a smaller secondary branch known to science as the Orion arm or the Orion spur, situated comfortably between the larger Sagittarius and Perseus arms. This location is roughly halfway between the crowded center and the sparse outer edge of the disk, about 27,000 light-years away from the core. It is a relatively serene and quiet neighborhood, not too heavily congested with stars, safely removed from the dangerous radiation fields near the center, and not so far out that the density of matter drops too low. In cosmic terms, it is an incredibly stable and fortunate address for life to flourish. The disk itself is not a single uniform layer, it is structured with distinct features. There is a thin disk that holds the vast majority of the gas and younger stars, and a thicker disk that houses older stars travelling on slightly different orbits. Surrounding both of these layers is the halo, a massive spherical distribution of scattered stars and dark matter that reaches far beyond the boundaries of the visible disk. This halo is home to ancient globular clusters, each a tightly packed ball containing hundreds of thousands of stars orbiting the galaxy like miniature satellites. The halo also contains the vast majority of the galaxy's dark matter, which remains entirely invisible, but is absolutely essential for keeping the structure bound together. Without this hidden mass, the stars travelling in the outer disk would simply drift away into the void. Instead, they remain bound, orbiting much faster than they otherwise should. This stands as elegant proof that unseen matter heavily outweighs the visible stars. The true scale of this architecture is incredibly difficult to visualize. A single light year represents roughly 10 trillion kilometers. To cross the entire disk of the Milky Way at the speed of light would require a journey of 100,000 years. Traveling at the speeds of our fastest modern spacecraft, it would take billions of years. This means that from one side of our galaxy to the other, stars are separated by distances so immense that even imagining travel between them is completely daunting. Yet within this colossal disk are hundreds of billions of stars, the vast majority hosting their own planets, spread across the spiral arms like endless grains of sand on a beach. If you could look down at the Milky Way from high above, you would see these stars glowing in a majestic disk, brightest at the center and thinning out toward the edges, threaded through by dark lanes of cosmic dust that absorb the starlight. The galaxy would appear magnificent yet delicate, a luminous pinwheel suspended gracefully in the absolute darkness of space. The size of the Milky Way is not just a spatial dimension, it also functions as a profound timekeeper. Our solar system completes a single loop around the centre of the galaxy once every 230 million years. This means that in the entire 4.5 billion year history of our planet, the Earth has circled the galaxy roughly 20 times. When the dinosaurs walked the Earth, our planet was occupying a completely different quadrant of the galaxy than we are today. While continents drifted, life evolved, and civilizations rose, the solar system moved quietly along its orbit, carrying us smoothly through the spiral arms. Every single lap is so staggeringly long that entire species rise and fall in the time it takes to complete a single circuit. The scale of the Milky Way is measured not just in distance, but in the immense ages it takes to move through it. Furthermore, our galaxy is not a static structure. Its shape and size are constantly being influenced by interactions with neighbours. The Milky Way is currently in the process of consuming smaller dwarf galaxies, their stars being stretched out into long streams that weave through our halo. In about 4 billion years, the Milky Way will collide directly with the Andromeda galaxy, our nearest large neighbour. That titanic collision will completely reshape both structures, merging them over billions of years into a new, larger elliptical galaxy. For the time being, however, the Milky Way's geometry remains that of a stable barred spiral, stable enough that we can map it with confidence, but dynamic enough that grand change is inevitable in the deep future. One of the great challenges of mapping the Milky Way is that we can never step outside its borders to take a look. Instead, astronomers must rely on indirect methods. By plotting the positions and speeds of stars, tracking the distribution of hydrogen gas with radio dishes, and studying how dust absorbs light. They build a highly accurate picture of the disk. The Gaia spacecraft has been revolutionary in this effort, measuring the precise locations and velocities of more than 1 billion stars with incredible accuracy. With this data, scientists can trace the paths of the spiral arms, measure the true thickness of the disk, and even detect subtle ripples caused by past galactic encounters. The result is a map that, while still a work in progress, gives us the best view yet of our galaxy's true shape. The boundaries describing the size of the Milky Way are precise, yet they are also highly flexible because the edges of a galaxy are not sharp or rigid. Unlike a planet with a distinct physical surface, a galaxy fades out gradually into the darkness of space. Stars become increasingly sparse, and gas clouds become thinner until eventually, the line between the galaxy and intergalactic space blurs completely. Estimates of the Milky Way's size depend entirely on whether you choose to measure only the bright visible disk, which is about 100,000 light-years across, or choose to include the vast dark matter halo, which can extend for 300,000 light-years or more. In that sense, the true structure of the Milky Way is significantly grander than its visible stars suggest, its true size hidden inside an invisible envelope. Contemplating this shape and size can easily feel overwhelming to the human mind, but there is a deep comfort in letting these details settle slowly. The Milky Way is not an abstract, cold scientific object. It is the protective home that holds our sun, our planet, and the entirety of human history. Its spiral arms are the pathways along which new stars are born. Its halo is the protective shield that keeps the entire system together. Its central bar and bulge serve as the gravitational anchor around which everything we have ever known orbits. To know its shape is to understand the architecture of a home. To comprehend its size is to appreciate the scale of the magnificent stage upon which all of human existence has unfolded. Picture yourself once more standing beneath the night sky, looking up at that hazy band of the Milky Way. Now, instead of viewing it as a simple ribbon of light, visualize the full majestic disk stretched out above you, 100,000 light-years wide, arms curling gracefully outward, stars scattered by the hundreds of billions. Imagine our own sun as a single, microscopic point of light, circling slowly in the quiet neighbourhood of the Orion Arm. Imagine that all around you, hidden from your eyes, is a colossal halo of stars and dark matter extending 3 times farther out than the visible disk itself. The night sky is transformed from a random collection of lights into the magnificent inside view of a vast spiral system, a home so monumentally large that it requires hundreds of millions of years just to complete a single orbit. As that picture forms clearly in your mind, notice how the Milky Way becomes familiar. It is no longer just a name or a pale glow. It is a real physical structure with a definitive shape, size, and features. It is thin, flat, and wide, featuring arms that emerge gracefully from a prominent central bar. It reaches across hundreds of thousands of light years if you choose to include the halo. It holds not just visible stars, but the massive, unseen presence of dark matter. It is not a static object, but an evolving, living system shaped by time, motion, and the pull of gravity. All of these details construct a map. And though we may never step outside the boundaries of our galaxy to look back and view it directly, our minds can hold that map, turning it over gently in our thoughts until it feels entirely familiar and soothing. Let us choose to stay with this comforting picture of home a little longer. A barred spiral 100,000 light years across, featuring arms, a bulge, a halo, and a central black hole, housing hundreds of billions of suns. This is exactly where we live. This is the true shape and scale of our galaxy. Now that we have fully settled into the layout of the Milky Way, it feels entirely natural to lift our gaze a bit further outward, exactly as if we were stepping off the front porch of our house to admire the neighbourhood surrounding us. A galaxy on its own is already monumentally immense, but it does not float through the void of space in absolute isolation. It belongs to a community of galaxies, groups bound tightly together by gravity, drifting and circling in beautiful patterns that play out over billions of years. The moment we begin to picture that neighbourhood, the Milky Way transforms into a single member of a larger family, and the scale of our cosmic surroundings expands once more. Tonight, let us take a slow, peaceful walk through that cosmic neighbourhood, first placing the Milky Way inside its local group, and then following the invisible threads that connect galaxies into even grander structures. The most immediate neighbour to the Milky Way is the Andromeda galaxy. This is the closest major spiral system to our own, though it is slightly grander in size, and it sits roughly 2 million light years away. That distance is completely staggering by human standards, but in cosmic terms, it makes Andromeda practically next door. If our galaxy is a house, Andromeda is the neighbour across a wide field, visible through the trees, but still close enough to notice. In fact, Andromeda is visible to the naked eye from Earth on clear, dark nights, appearing as a faint smudge in the sky. Through telescopes, it reveals itself as another barred spiral filled with hundreds of billions of stars with arms and dust lanes, much like the Milky Way. Knowing that such a vast system hangs quietly in our sky is one of the most grounding realizations astronomy can offer. The smudge you see is not just a patch of light. It is an entire galaxy comparable in size and structure to our own waiting across the void. Alongside Andromeda and the Milky Way are smaller companions. These are dwarf galaxies, less massive but still important parts of the neighbourhood. The Large and Small Magellanic Clouds are two of the most famous, visible from the southern hemisphere as irregular patches of light. These dwarfs orbit the Milky Way, their stars and gas slowly being drawn in by our galaxy's gravity. Streams of material extend from them, evidence of the tug-of-war between small and large systems. The Milky Way has dozens of such companions, faint dwarfs that circle like satellites. Many of them were discovered only recently as astronomers developed better surveys. Andromeda has its own collection of dwarfs too, creating a pair of galactic families facing one another across the intergalactic gap. Together, the Milky Way, Andromeda, and their satellites form the local group. This is the official name for our cosmic neighbourhood, a collection of more than 50 galaxies bound together by gravity. Most of them are dwarfs, faint and irregular, but the Milky Way and Andromeda dominate. Between them lies a balance of pull, a gravitational dance that will one day bring the two giants together. In about 4 billion years, the Milky Way and Andromeda will collide, merging into a single larger galaxy. For now, though, they drift toward one another, closing the gap at about 100 kilometers per second. A speed that sounds fast but will still take billions of years to complete. That slow inevitability is part of what makes the local group a true neighborhood. Its members are bound, not free to escape, moving together through space in patterns that can only be measured on cosmic timescales. The local group itself is not large by universal standards. It spans about 10 million light-years across, which is only a fraction of the observable universe. Within that volume, the galaxies are scattered, separated by millions of light-years of empty space. If you could step outside and look back, the local group would appear as a loose cluster with two bright spirals in the middle and a scattering of faint companions around them. It is not crowded like a city, but sparse like a rural landscape, with long stretches of darkness between glowing islands. This sparsity is part of the nature of galaxies. Even when they gather, the spaces between them remain vast, reminding us that emptiness is as much a part of the universe as light. Beyond the local group lies another layer of the neighborhood. The local group itself is part of a larger structure called the local sheet, a flattened region of galaxies that includes several nearby groups. Imagine the local group as one household and the local sheet as the street on which we live. Other groups, such as the M81 group and the Centaurus group, line this street, each with their own bright galaxies and faint companions. Together they form a pattern that is not random, but shaped by gravity, expansion, and the distribution of dark matter. The local sheet spans about 30 million light-years, and within it galaxies move slowly relative to one another, creating a sense of stability over billions of years. One of the most prominent structures near us is the Virgo cluster. This cluster lies about 65 million light-years away and contains more than 1,000 galaxies. It is the central hub of a much larger arrangement known as the Virgo supercluster, of which our local group is a tiny part. The Virgo cluster is a city compared to our small town, filled with galaxies packed closely together, interacting, colliding, and shaping one another. Some of the galaxies in Virgo are giant ellipticals containing trillions of stars. Others are spirals like ours caught in the gravitational web of the cluster. The cluster itself is held together not just by the visible galaxies, but by an even greater mass of dark matter, a reminder that what we see is only part of the picture. As astronomers mapped these clusters and groups, they began to see patterns on even larger scales. Galaxies are not scattered randomly through the universe. They are arranged in filaments and whorls, vast chains stretching across hundreds of millions of light-years. Between them lie voids, enormous regions almost empty of galaxies. The result is a structure known as the cosmic web, a pattern of light and darkness that resembles a sponge or a network of veins. Our local group lies on one of these filaments connected to larger structures that extend beyond what we can easily picture. In this web, galaxies are the bright nodes, groups are the intersections, and clusters are the hubs, all connected by invisible strands of dark matter and gas. This tour of our cosmic neighborhood is more than a list of names and distances. It is a way of placing ourselves within the hierarchy of the universe. At the smallest scale, we belong to the solar system orbiting our star. At the next scale, we are part of the Milky Way, orbiting the galactic center. At the next, we are members of the local group bound with Andromeda and dozens of dwarfs. Beyond that, we are part of the Virgo supercluster, which itself is just one piece of the larger Laniakea supercluster, a vast structure encompassing 100,000 galaxies. Each layer is both grounding and humbling, reminding us that our home is part of a system that grows larger and larger with every step outward. The word neighborhood can sometimes make the cosmos sound smaller than it is, but in truth, it is a useful way of thinking. Just as in the human neighborhood, some houses are close together, while others are farther apart. Some are small, some are large, some are tidy, some are crowded. And like neighborhoods on Earth, these galactic communities are not isolated. They interact, influence one another, and evolve together. Our cosmic neighborhood is defined not only by what galaxies are nearby, but by the ways in which their gravity links them, pulling them into patterns that will play out long after our species is gone. Standing under the night sky, you can remind yourself that everything you see is inside one galaxy. the Milky Way. But beyond that faint band are neighbours invisible to your eyes, too far and faint to appear without telescopes. The Andromeda Galaxy, the Magellanic Clouds, the faint dwarfs of the local group. They are all out there, silent companions in the dark. And beyond them, clusters and superclusters, filaments and voids, stretching into patterns so large that the mind can only begin to grasp them. Yet in all of this, the word neighbourhood still feels right. Because whether we are speaking of the house next door or the galaxy next door, the sense of belonging remains. We are not alone. We live in a community, one that is vast and ancient, but still a community all the same. As we finish this slow walk through our surroundings, the scale of the neighbourhood becomes clearer. The Milky Way is our home. Andromeda is the great neighbour across the way. Dozens of dwarfs are like smaller houses clustered nearby. Together they form the local group, which itself lies on the edge of larger clusters and filaments. Part of a supercluster, part of a web. Each step outward adds distance, but it also adds connection. A galaxy is not an island, it is one node in a vast network. And as we continue outward, we will see that this network extends not just across our local patch, but across the entire observable universe. A neighbourhood so large that it becomes the universe itself. When we talk about galaxies, the numbers quickly become overwhelming. Hundreds of billions of stars, trillions in the larger systems, and more still when we zoom out to the universe itself. But to make sense of such scales, it helps to slow down and focus on one question at a time. Rather than trying to picture all the galaxies scattered across the universe, let us pause here in our own backyard and think carefully about the stars that fill just our galaxy. Counting the stars of the Milky Way is not something that can be done with a tally sheet and a telescope. It is a task that blends measurement, estimation, and imagination. And while the exact number remains uncertain, the process of arriving at it is as fascinating as the number itself. Tonight, let us count the stars, not by naming them one by one, but by following the methods that allow astronomers to take something so vast and turn it into something we can describe. The first thing to acknowledge is that no one has ever counted every star in the Milky Way. Even if we could, many of them are too faint to see with any telescope we currently have. Stars like our Sun are bright enough to be visible across great distances, but red dwarfs, which make up the majority of stars, shine so dimly that they blend into the background. In addition, clouds of dust obscure large regions of the galaxy, blocking visible light and making the count even more difficult. So when we talk about counting stars, what we really mean is estimating their number based on models of how stars are distributed and how galaxies behave. It is a little like trying to estimate the number of trees in a forest by standing in one part of it, counting what you see, and then applying that average to the entire area. You cannot see every tree, but you can still come to a reasonable figure. Astronomers approach this problem in several ways. One method is to measure the mass of the Milky Way. By estimating how much mass the galaxy contains, and then dividing by the average mass of a star, they can arrive at an approximate number of stars. Of course, not all of the galaxy's mass is in stars. Some of it is in gas, dust, planets, and the dark matter that outweighs everything else. But by subtracting what is not starlight, scientists can get closer to the true figure. This approach suggests that the Milky Way contains between 200 and 400 billion stars. That is a range, not a precise number, but it is accurate enough to give us a sense of the scale. 200 billion is already beyond comprehension. 400 billion doubles it, making the galaxy feel even more crowded. Somewhere within that range lies the truth. Next, let us choose to pause our outward march for a moment and rest with these stars. Another reliable approach is to count stars inside targeted sectors of the cosmos, and then extrapolate that data across the wider system. By meticulously auditing tiny patches of the night sky, researchers can document the quantity and stellar classification of suns inside that localized zone, using those insights to build a comprehensive model of the broader disk. This specific process demands a deep comprehension of how stellar populations are organized according to their age and category. For instance, younger generations of suns are heavily concentrated within the swirling spiral arms, whereas ancient stellar populations are far more common inside the core bulge and surrounding halo. Dim red dwarfs represent the absolute majority in terms of sheer numbers, but they contribute very little to the galaxy's overall light output. Conversely, hyperluminous giants and supergiants are incredibly rare anomalies, yet they blaze with enough brilliance to illuminate entire sectors. By synthesizing all of these dynamic variables, scientists are able to formulate what is known as the initial mass function. This serves as a mathematical recipe detailing exactly how many stars of varying physical dimensions ought to exist throughout the system. Deploying that formula across the map allows for an accurate population assessment, even if our technology cannot physically see every individual star. To ground this concept in simpler terms, picture yourself standing inside a massive packed stadium at night. From your specific vantage point, you can clearly identify the spectators sitting closest to you. If you pick up a pair of binoculars, your vision reaches much further, but even with the absolute best vantage point, directly counting every person in the bleachers remains impossible. Instead, you would likely count the individuals in one distinct seating section, and then assume the rest of the stadium is filled in an identical fashion. That calculation will certainly not be flawless, but it will provide an accurate estimate to describe the total crowd. Auditing stars across our galaxy works in the exact same manner, except the stadium we are measuring spans 100,000 light-years across, and the spectators are hundreds of billions of blazing suns. One of the most startling revelations of this process is discovering just how many stars shine too faintly to ever be noticed. The most radiant landmarks in our night sky, the famous entities we identify by name, represent a microscopic fraction of the grand total. The overwhelming majority of suns inside the Milky Way are incredibly dim red dwarfs, objects that are significantly cooler and smaller than our Sun, emitting so little light that they remain completely invisible without advanced telescopes. These red dwarfs comprise roughly 3/4 of the entire stellar population. Imagine if you possessed the power to suddenly extinguish all the brilliant stars and observe only these red dwarfs. The night sky would still be completely saturated, but it would glow with an incredibly soft, subtle light. Now, picture the exact opposite scenario. If those red dwarfs were to instantly vanish, the heavens would look almost entirely desolate. The galaxy is incredibly crowded, but its true density is masked by its faintest lights. Another layer of complexity stems from the fact that stars are not distributed evenly across space. Certain regions of the Milky Way are heavily congested, such as the central core bulge where suns are packed together in tight quarters. Other environments, like the outer rim of the disk, are dramatically more sparse. There are distinct stellar clusters scattered throughout, including open clusters holding young star families and globular clusters packed with ancient suns. There are majestic stellar nurseries where dense clouds of gas are actively moulding newborn stars, and stellar graveyards where cataclysmic supernovas have left behind skeletal remnants. Counting stars means more than just tallying up a ledger. It requires a deep understanding of how they are arranged, mirroring a sprawling city with neighbourhoods that vary wildly in population density. Some avenues are tightly packed with houses, while other suburbs feature massive stretches of open land. Our galaxy boasts that exact same structural variety. One might naturally wonder, why does calculating this population matter in the grand scheme of things? On one hand, the final metric itself is far less significant than the brilliant scientific journey required to reach it. But knowing the exact volume of stars helps astronomers decode the total mass of the galaxy, map out its evolutionary history, and calculate the statistical likelihood of planets and life. If the Milky Way holds upward of 400 billion stars, and if even a tiny percentage of them are orbited by planets sitting inside habitable zones, the total number of Earth-like worlds is absolutely immense. Even if the vast majority of them turn out to be completely barren, the mathematical probability of alien life multiplying elsewhere scales up with every single star we add to the global tally. In this manner, counting stars ceases to be a dry numerical exercise. It transforms into a way of calculating our true odds of having company in this silent cosmos. It is also an elegant way to appreciate our unique place in the universe. Out of hundreds of billions of available stars, our planet orbits just one. Realizing that our Sun is merely a single point among an infinity of others, can make it seem entirely ordinary. Yet to our eyes, it is completely extraordinary. The vital anchor that provides us with light and sustains all life. In this sense, calculating the stars is deeply humbling, but it is also profoundly reassuring. The galaxy is a vast ocean of suns, but this specific one belongs to us. It keeps us safely anchored right in the center of a brilliant sea of light. The advanced instruments astronomers utilize to count these stars are works of art on their own. Comprehensive cosmic audits like the Sloan Digital Sky Survey and the landmark Gaia mission yield incredibly detailed maps of stars peppered across the heavens. Gaia in particular has tracked the precise locations and orbital movements of over 1 billion individual stars, creating a masterpiece three-dimensional map of our Milky Way. Armed with this data, researchers can refine their mathematical models, narrowing the margin of error for our global totals. Yet even with this level of technological precision, massive uncertainties persist. Heavy dust clouds completely hide entire star clusters from our line of sight. Calculating exact distances becomes an extraordinary obstacle when dealing with stars sitting on the far edge of the galactic disk. The galaxy is simply too monumentally vast for any human survey to ever be fully complete. Therefore, a metric of 200 to 400 billion remains the most accurate estimate science can offer. It serves as a gentle reminder that even with our most advanced instruments, the universe fiercely guards its mysteries. Think once more about standing outdoors beneath the open night sky. From your vantage point on Earth, without the aid of a telescope, you can only see roughly 6,000 stars across the entire celestial sphere. That is the absolute limit of the unprotected human eye. If you pick up a basic pair of binoculars or a small backyard telescope, thousands more suddenly jump into view. With massive professional observatories, we can resolve millions. But even then, you are only ever witnessing the most microscopic slice of the genuine total. Picture a massive jar filled with an ocean of marbles, so many that physically counting them one by one would take a lifetime. Instead, you might scoop out a single handful, count the marbles in your palm, and then multiply that number by the total number of handfuls required to fill the container to the brim. That is exactly how the stellar population of the Milky Way is calculated. It is not a literal one-by-one tally, but a deeply informed estimate, firmly rooted in direct observation and guided by robust astrophysical theory. There is a distinct, poetic beauty in the fact that we can never pin down the exact number. Our galaxy is simply too vast, too complex, and too deeply saturated with hidden light for humanity to ever compile a perfect catalogue. And yet, we can still describe its boundaries with confidence, outline its grand structural limits, and state that hundreds of billions of suns share this magnificent spiral with us. That beautiful balance between accepting our lack of absolute precision while still understanding the grand architecture is the true magic of astronomy. It reminds us that the cosmos is not a simple riddle to be solved and discarded, but an endless landscape destined to be explored one estimation at a time. If our lone galaxy holds that many stars inside its borders, what happens when we place it among the billions of other galaxies floating across the universe? The numbers begin to multiply exponentially until they climb to heights our minds cannot comprehend. But before we take that giant mental leap, it is well worth lingering right here in our own galactic backyard, respecting the stars that immediately surround us. Every single one is a blazing sun. Each carries its own unique history, and together they construct the radiant, glowing body of the Milky Way. Counting them may be a practical impossibility, but grasping their sheer abundance grants us a far deeper comprehension of where we reside. We are not drifting blindly through a cold vacuum. We are deeply embedded inside a brilliant sea of light, a sea so monumentally wide that even the word billions starts to feel incredibly small. When we visualize the Milky Way, our minds naturally prefer to imagine something with clean, defined edges. We like to think of it the way a map of a country has bold borders drawn clearly along its frontiers. Human psychology craves rigid boundaries because they make the physical world much easier to categorize and describe. But galaxies do not behave like human countries or cities. They do not possess sharp physical outlines, nor do they feature fences marking exactly where their territory stops and the empty vacuum of space begins. Instead, they fade out in an incredibly gradual gradient, their stellar populations thinning out step by step, and their gas clouds becoming increasingly sparse until the distinction between the galaxy and the grand universe blurs into nothingness. Because of this, answering the question of exactly where our galaxy ends is an incredibly subtle challenge. It is one of those inquiries that appears perfectly simple on the surface, but reveals immense depth the longer you ponder it. Tonight, let us take all the time we need to explore how modern astronomers attempt to crack this puzzle. What does it truly mean for the Milky Way to have an outer edge, and what wonders wait beyond that frontier in the vast open void separating galaxies? The most logical starting point for our exploration is the central disk. The Milky Way is a classic barred spiral spanning roughly 100,000 light-years across its primary visible disk. This disk is a structural zone where the absolute majority of stars, dust lanes, and gas reservoirs reside, all concentrated in a flat plane with elegant spiral arms curling outward from the core. If you choose to define our galaxy solely by the boundaries of this disk, you could state that it officially ends at the exact location where the stars become too sparse to maintain a cohesive, continuous structure. But even that metric does not yield a clean, sharp line. Stars continue to exist well beyond the bright perimeter of the primary disk, thinning out in a slow gradient, but remaining undeniably present. Strands of stellar dust and stray gas trails bleed far out into the surrounding darkness. So while scientists use the convention that the disk is 100,000 light-years wide, that number is a helpful agreement rather than a rigid physical wall. The outer edge of the galactic disk functions exactly like the shifting shoreline of a beach at low tide, constantly fluid, perpetually fading, and always uncertain. Moving beyond the boundaries of the disk, we encounter the vast domain of the halo. This halo is a colossal, roughly spherical cloud that completely envelops the flat galaxy, holding scattered stars, ancient globular clusters, and massive reservoirs of invisible dark matter. Unlike the flat disk, the halo possesses no clear physical edge whatsoever. Its component stars become increasingly sparse and faint the further you travel from the core, but they never abruptly stop. Certain lone stars inside the halo complete orbits that take them hundreds of thousands of light-years away from the galactic center. Globular clusters, those dense, ancient knots of tightly bound suns, are discovered floating far outside the primary disk. Furthermore, the dark matter component of this halo reaches out even further, potentially spanning 2 or 3 times the total radius of the visible galaxy. If you choose to calculate the Milky Way's size by the boundaries of this halo, our home galaxy may span 600,000 light-years across or even more. That makes it 6 times larger than the dimension of the disk alone, even though the vast majority of this domain is completely invisible to our eyes. So, looking at this intricate blueprint, where would you draw the final line? Do you place it at the border of the bright disk, at the location of the absolute furthest halo stars, or at the maximum reach of the invisible dark matter envelope? Every single definition yields a completely different dimension. To bypass this ambiguity, astronomers frequently rely on a metric known as the virial radius to define the functional edge of a galaxy. This radius represents the exact spatial boundary within which the galaxy's own internal gravity remains the dominant force keeping objects physically bound to the system. The moment an object travels past this virial radius, the gravitational pull of neighbouring galaxies and the macro expansion of the universe becomes stronger, meaning the object can no longer be categorized as part of our system. For the Milky Way, this critical virial boundary is calculated to sit roughly 250,000 light-years away from the core. Absolutely everything residing inside that perimeter is legally considered a bound member of our galaxy. Everything sitting beyond it belongs to the open medium of intergalactic space, or falls under the gravitational domain of an entirely separate system. Even this mathematical boundary is not completely absolute, because galaxies are constantly moving and their massive outer halos can easily overlap and blend together. but it provides a reliable method for assigning the galaxy a definitive size based on the laws of gravity. We can also choose to look at the galaxy's edge through the lens of pure motion. Stars locked inside the primary disk complete well-defined, predictable, circular orbits around the central hub. Stars scattered out in the halo also orbit the core, but they travel along highly elongated, erratic tracks that can fling them incredibly far into the dark outskirts. At a certain point, a star's trajectory can become so intensely stretched that it snaps its bonds entirely, pulled away by the passing gravity of a neighbouring system or swept up by the expansion of space itself. When that cataclysmic event occurs, the star is no longer tethered, it transforms into a rogue wanderer, travelling endlessly through the intergalactic void. In this specific light, the edge of the galaxy is defined as the absolute limit of gravitational binding. Everything sitting inside is securely tied to the Milky Way, while everything sitting beyond is entirely free. Our home galaxy is not an isolated entity in this vast picture. The Milky Way and its cosmic twin, Andromeda, along with their retinue of smaller satellite systems, are securely tethered to one another inside a cosmic neighbourhood known as the local group. The outer boundaries of their massive halos may actually intersect and mingle, producing an ambiguous frontier zone where it is incredibly challenging to determine exactly which parent galaxy a specific celestial body belongs to. Viewed in this light, the edges of these massive stellar islands are not just fuzzy, they are explicitly shared. Just as separate towns in a densely populated geographic region can expand and seamlessly bleed into one another without a strict physical dividing line, galaxies within a communal group can overlap, allowing their outer borders to freely intermingle. When the unavoidable collision between the Milky Way and Andromeda takes place in approximately 4 billion years, their outer boundaries will blend together completely, ultimately fusing the two independent structures into a single massive system over the course of aeons. When that transformation occurs, any previous definition of where the Milky Way officially ends will be rendered obsolete, because the individual galaxy we inhabit today will cease to exist in its current form. This distinct lack of a sharp, clean edge can sometimes feel a bit frustrating to our human desire for order, but it is a fundamental aspect of what makes galaxies so beautiful. They are not fixed, rigid monuments carved out of stone with permanent, unyielding dimensions. Instead, they function as dynamic, living systems perpetually moulded by time, the laws of gravity, and cosmic encounters. Their component stars are ignited deep within the dense flat disk, slowly drift outward into the sprawling halo over time, and occasionally manage to escape from the system's gravitational grid altogether. Their vital gas reservoirs are continually pulled inward to fuel new star formation, blown outward by energetic feedback, stripped away during violent near misses with other systems, and replenished by the explosive deaths of dying suns. Their invisible dark matter halos stretch outward over immense distances, quietly blending into the dark envelopes of neighbouring systems. The Milky Way does not stop abruptly the way a brick wall ends. It fades out into the void in a smooth gradient, precisely like the warm light of a campfire growing fainter and weaker as you slowly walk away from the flames into the darkness until its presence is ultimately indistinguishable from the background night. This reality introduces a deeply fascinating insight. The true boundary of the Milky Way is entirely dependent on the specific tools and perspective of the observer. To our naked eyes on Earth, the galaxy manifests purely as a concentrated, pale ribbon of light, cutting across the sky, and its edge is defined as the exact point where individual stars grow too dim for our vision to process. But the moment you point an optical telescope at the heavens, that perceived edge extends significantly further out into the dark. If you swap that instrument for a professional radio telescope, the boundary stretches further still, because radio dishes can easily trace vast clouds of neutral hydrogen gas in quiet sectors where visible stars are completely absent. Furthermore, if you rely on complex gravitational measurements, the functional border expands to the ultimate perimeter of the invisible dark matter halo. Every unique scientific instrument draws a completely different line on the map, not because the physical galaxy has altered its shape, but because our method of perceiving its architecture has shifted. In this manner, the true termination point of the galaxy is just as much a reflection of our technological tools and vantage point as it is a characteristic of the cosmic object itself. It can be incredibly helpful to compare this phenomenon to the behavior of the Earth's atmosphere. Where does our planet's atmosphere officially stop and open space begin? Down at sea level, the air molecules are incredibly dense and tightly packed. As you rise higher into the sky, the air thins out in a steady gradient until you reach an altitude where conventional airplanes can no longer find enough lift to fly. Travel higher still, and astronauts begin to experience weightlessness in orbit, yet delicate instruments can still detect stray atmospheric molecules brushing against the spacecraft. Depending on the specific scientific or operational goal, researchers choose to define the official boundary of space at several different altitudes, such as the conventional Kármán line at 100 kilometers or even higher up. But the ultimate physical truth is that the atmosphere fades out in a gradual, continuous transition without a single sharp boundary. Our galaxy follows that exact same blueprint. It features core regions where stellar populations are intensely dense, vast outer domains where stars are exceptionally sparse, and peripheral boundary zones where its components smoothly dissolve into the background vacuum. To ask where it definitively ends is to embrace the reality that the answer is entirely determined by how you choose to define the parameters of your search. This beautifully gradual fading is not merely a quirk of its current structure, it is a direct reflection of the galaxy's long history. Over the course of billions of years, the Milky Way has expanded its domain by systematically accreting smaller independent dwarf systems, pulling their stars and gas into its own halo. Even today, distinct, coherent streams of stars can be mapped, tracing the orbital pathways of these ancient galactic meals, winding around our system like faint stellar rivers. These structural streams can reach out incredibly far beyond the visible boundaries of the primary disk, dynamic reminders that the Milky Way is still actively growing, still in the very middle of defining its final structure. In this light, the edge of our galaxy is not a fixed factor because the galaxy itself is fundamentally unfinished. It exists as an ongoing project, perpetually expanding, continuously absorbing material, and always changing. Reflecting deeply on where our galaxy ends can also profoundly shift how you view your personal place within its architecture. If you choose to visualize the galaxy as a neatly boxed, sharply bounded disk, then our solar system feels like it is securely locked deep inside an interior room, with a clear and distinct wall separating us from the grand outside world. But if you instead visualize the galaxy as a beautifully fading, continuous system with stars and invisible mass stretching outward indefinitely, the arbitrary boundary between the inside and the outside vanishes entirely. We are not safely enclosed within rigid artificial walls. We are an active part of a beautiful continuum that stretches out seamlessly into the grander universe. The Milky Way does not abruptly stop and then hand over the reins to the rest of the cosmos. It is the cosmos itself, beautifully woven into it and merging with it without a single hard dividing line. This expansive perspective can be incredibly soothing to the mind. The psychological craving for sharp, rigid boundaries is a natural human instinct, a practical survival mechanism we use to simplify a complex world into neat, digestible categories. But the macro-universe is simply not constructed that way. It is fundamentally built on elegant gradients, continuous transitions, and smooth continuums. The outer borders of galaxies are soft and fluid. The limits of massive galactic clusters are soft. Even the ultimate boundary of the observable universe is not a solid physical wall, but a shifting cosmic horizon beyond which light has simply not had enough time to reach our eyes. Everywhere we direct our instruments, the universe fiercely resists being boxed into rigid categories, and that resistance is not something to find frustrating. It is incredibly freeing. It signifies that the cosmos is fundamentally larger, more open, and more beautifully continuous than any of our rigid human categories can ever hope to contain. As we choose to linger comfortably on this thought, the Milky Way transforms from a cold, static object into a magnificent living system. Its primary disk spins smoothly through the void, its elegant arms curve gracefully across space, and its hundreds of billions of suns complete their long orbits. Its massive halo reaches out invisibly into the dark. Its historical streams of stars preserve the ancient pathways of long-lost mergers. Its interstellar gas clouds perpetually give birth to new generations of suns. And its central supermassive black hole provides the gravitational anchor for the entire structure. Not a single one of these structural features possesses a sharp, rigid edge. All of them beautifully blend into one another, overlapping, interacting, and changing over cosmic time. To genuinely ask where our galaxy ends is to realize the ultimate truth. It never truly does. It merely fades out, gracefully dissolving into the grander universe, serves as a gentle reminder that absolutely nothing in this cosmos is ever truly separate from the whole. The Milky Way is not a locked, closed container. It is a magnificent, open architecture defined by a flat disk, a sprawling halo, and a massive gravitational reach. It officially ends only at the point where stars can no longer maintain a bound orbit, where its internal gravity loses its grip, and where its collective light can no longer illuminate the dark. But even at that extreme frontier, its physical influence reaches further still, overlapping with its cosmic neighbours, blending into local clusters, and linking up with the grand filaments of the cosmic web. Its outer edge is not a final ending, it is a transition. And in that continuous transition, we witness the exact method by which the entire universe is constructed, not as a fragmented collection of detached, separate objects, but as a single, beautifully interconnected web of parts, with each element gracefully fading into the next. When we last left off our exploration, we were reflecting deeply on exactly where the Milky Way ends, and how its outer frontiers behave less like rigid walls and more like beautifully fading transitions. That realization naturally steers our curiosity toward the very next logical step outward on our journey. If our home galaxy slowly dissolves into the deep void of space, what spectacular reality waits in the massive gulf separating our system from the next? What exactly is the true nature of the grand gap between galaxies? And what entity fills those monumentally immense stretches of absolute darkness? On a perfectly clear night, looking up at the majestic band of the Milky Way, or identifying the tiny faint smudge of Andromeda, it can easily feel like the heavens are completely overflowing with stars. But that visual impression is an illusion born from the fact that we are currently locked deep inside a dense stellar island, surrounded by hundreds of billions of local suns. The moment you choose to step outside those borders in your imagination and attempt to visualize the true distance separating one galaxy from another, the true emptiness of the cosmos becomes starkly apparent. Tonight, let us take a slow, peaceful walk across those massive intergalactic spaces, refusing to rush and allowing the true vastness of the void to reveal itself in a gentle gradient. The first crucial truth to wrap our minds around is the staggering physical scale of the gap itself. Our closest large galactic neighbour, Andromeda, is situated roughly 2.5 million light-years away from us. While it is legally the closest major system in the entire cosmos, that number completely stretches human imagination to its absolute limits. Light, which travels at the absolute maximum speed limit allowed by the laws of physics, still requires a staggering 2.5 million years just to complete the journey across that gulf. This means that when you align a telescope and peer at Andromeda, the photons entering your eyes left that galaxy long before the human species had even evolved on Earth. If you attempted to cross that identical gap, travelling aboard our fastest modern spacecraft, the journey would require tens of billions of years, a duration longer than the universe itself has existed since the Big Bang. Andromeda is right next door in cosmic terms, but it is unimaginably far away on any human scale. Between our home and that neighbour sits no dense sea of stars and no clutter of planetary systems, but mostly empty space. However, the word empty does not mean that these intergalactic zones are a state of perfect absolute nothingness. The vast space separating galaxies is not a flawless vacuum. It contains millions of stray rogue stars that were violently flung out into the void during ancient galactic collisions, or systematically stripped from their parent orbits by intense gravitational tides. These isolated stars drift through the intergalactic medium completely alone, shining in total solitude and sitting far too distant from any major galactic shoreline to ever be considered a part of one. They are exceptionally rare anomalies when compared to the hundreds of billions of suns securely packed inside galaxies, but they are still numerous enough across the macro scales to ensure that the intergalactic medium is not completely, totally dark. Alongside these lonely wanderers are colossal clouds of pristine gas, predominantly hydrogen, spread incredibly thin but reaching across vast domains. This intergalactic gas is so thoroughly diffuse that even in sectors boasting the highest concentration of matter, it would still represent a more perfect vacuum than the absolute best conditions we can manufacture inside advanced laboratories on Earth. Yet when you mathematically sum this matter up over the course of millions of light years, the gas adds up to a staggering total, filling the massive gaps with a faint, subtle presence. In fact, astrophysicists believe that the absolute majority of all the ordinary matter in the universe exist in this exact diffuse state, quietly hiding in the spaces between galaxies rather than tucked inside them. There is also an ambient sea of radiation permeating every single cubic centimetre of this space, the faint ancient afterglow of the Big Bang, known to science as a cosmic microwave background. No matter where you choose to drift in the vast gulfs between galaxies, this background hum is undeniably present, an eternal relic echoing the very birth of the universe. And underlying absolutely everything is the omnipresent scaffold of dark matter, completely invisible and entirely undetectable to our eyes, except through its powerful gravitational influence. This mysterious dark matter forms massive halos around individual galaxies and weaves colossal filaments that connect them across space, stretching through the empty gaps like an invisible cosmic scaffolding. So while the space separating galaxies appears to be a total void, it is actually threaded through with unseen architecture, saturated with diffuse gas, dotted with scattered rogue stars, and filled with ancient radiation that has been travelling across the cosmos since the dawn of time. To truly grasp the scale of this intergalactic emptiness, it is incredibly helpful to mentally scale the entire Milky Way down to the physical dimensions of a standard dinner plate. On that exact scale, the Andromeda Galaxy would manifest as another dinner plate sitting roughly 4 meters away from yours. In the space separating those two plates, there would be absolutely nothing but open air. The individual plates themselves would be densely packed with hundreds of billions of glowing grains of light representing stars. But the vast space separating them would be completely bare. That is the stark physical reality of galaxies. They exist as dense, localized islands of stars, floating in a monumentally vast cosmic ocean, separated by expanses so incredibly wide that the individual islands appear completely isolated from one another. When 20th century astronomers first realized that the Milky Way was merely a single specimen among a vast sea of galaxies, this specific realization was part of what struck them most forcefully. Not only were there countless other galaxies out there, but the raw distances separating them were absolutely enormous, vastly dwarfing the sizes of the galaxies themselves. This monumental scale explains exactly why galaxies rarely experience direct collisions despite their staggering numbers throughout the cosmos. Locked deep inside a single galaxy, stars can be packed relatively close to one another compared to interstellar distances, even though they are still separated by light years. But in the spaces separating independent galaxies, the gaps are so wide that even when they reside inside dense clusters, direct head-on smash-ups are remarkably rare events. Over the course of billions of years, gravity can slowly pull massive galaxies toward each other, and when they do eventually merge, Individual stars are flung wildly around like brilliant sparks, but that entire process unfolds across vast stretches of time. The overwhelming majority of the universe's long history is spent with galaxies drifting quietly and peacefully inside their allocated domains, not crashing violently into one another. These massive gaps function as vital cosmic buffers, granting every individual galaxy ample room to evolve and change on its own terms for eons before gravitational interactions reshape its structure completely. The intergalactic medium, though incredibly faint, is far from being a static or dead environment. It is continually heated by energetic quasars, active galactic nuclei whose central supermassive black holes aggressively swallow matter and pour out titanic torrents of energy across the universe. It is heavily salted and enriched by supernovas, which violently eject heavy elements and metals out of parent galaxies deep into open space. It is stirred and churned by the physical motion of massive galaxies ploughing through it, leaving behind complex hydrodynamic trails and wakes. In recent years, astronomers have utilized advanced X-ray and ultraviolet space telescopes to meticulously study this medium, successfully detecting the incredibly faint glow of superheated gas resting in the spaces between galaxies. These groundbreaking observations confirm that the universe is not a sterile vacuum, but a highly complex and dynamic environment, even in its absolute emptiest sectors. The gaps are a vital part of the cosmic story, not just blank spaces on a map. They preserve the raw material that will one day serve as the fuel to birth future galaxies and stars, slowly falling inward under the pull of gravity or gathering along massive filaments. The scale of these intergalactic gaps expands to an even more staggering degree when we venture beyond the local neighbourhood. Between our small local group and the dense Virgo cluster sits an absolute gulf of roughly 60 million light-years of space. That represents a journey of 60 million years travelling at the absolute speed of light, a massive chasm that completely dwarfs the distance separating us from Andromeda. These immense intercluster voids represent some of the most thoroughly empty environments in the entire known universe, with only a tiny handful of stray lonely galaxies scattered across their massive domains. They function precisely like vast cosmic deserts, punctuated occasionally by brilliant oases, where galaxies gather together in highly concentrated groups. When modern cosmologists map out the large-scale architecture of the universe, they discover a striking truth. These massive voids completely dominate the landscape. The vast majority of the universe is not filled with brilliant galaxies, but with immense emptiness. The galaxies themselves are confined to narrow filaments and walls, tightly surrounding the massive empty voids, exactly like layers of foam resting on the surface of water. Emptiness is not the exception to the rule in this universe, it is the rule. And yet, these immense intergalactic chasms are far from being a hostile void. They are simply monumentally spacious. They serve as the great canvas upon which all galaxies exist, providing the stark background contrast that makes localized clusters stand out so brilliantly. Without this profound emptiness, the radiant energy of the cosmos would possess no definition, and its megastructures would have no shape. In a very real sense, these open expanses give the universe its architectural form just as much as the visible galaxies themselves do. They provide the deep silence that makes the music of the stars audible, and they offer the dark background that brings structural groups into clear view. They serve as an eternal reminder that space is not a congested highway, but an exceptionally spacious realm, proving that the cosmos is not filled to the brim with matter, but is spread incredibly thin, featuring isolated islands of light separated by vast oceans of darkness. For those of us living deep within a crowded galactic disk, it is exceptionally difficult to genuinely feel the true emptiness of those intergalactic gaps. Our local sky is saturated with nearby stars, our telescopes reveal a staggering count of neighbouring galaxies, and our sensitive instruments detect radiation everywhere we look. But if you were somehow transported and placed directly in the dead centre of an intergalactic void, far away from any parent galaxy, your visual perspective would be radically different. The sky surrounding you would be almost completely and utterly dark. Only the most microscopic, faint smudges of distant galaxies would be visible to your eyes, scattered incredibly thin across the boundless void. There would be no magnificent Milky Way band cutting through the night, no familiar stellar constellations to guide you, and absolutely no sense of cosmic crowding. The complete silence of that isolated environment would be absolute, and its emptiness would feel nearly overwhelming. And yet, even in that desolate space, the cosmic microwave background would still hum its ancient tune, diffuse intergalactic gas would still wrap around you, and the invisible filaments of dark matter would still stretch out their scaffolding. The emptiness would not be absolute, it would be subtle, filled with the quietest whispers left behind long after the loudest voices have gone. This sweeping perspective fundamentally changes how we view our own home galaxy. The Milky Way may feel like a heavily populated city to us, but in the grander scheme of things, it is merely a lone island surrounded by a vast, dark ocean. Its light cuts through the void precisely because of the absolute darkness that envelops it, and its presence holds meaning because of the monumental gap that isolates it from its peers. Without these spatial gaps, independent galaxies would blur together into a uniform mass, and the universe would completely lose its beautiful layout. With them, the cosmos transforms into a brilliant pattern of islands and oceans, dense clusters and empty voids, radiant light and deep silence. The gap separating galaxies is far from being a design flaw. It is the vital space that makes the entire blueprint possible in the first place. When we reflect deeply on this, the emptiness ceases to be intimidating. It transforms into a beautiful reminder of true scale. It tells us that the universe is grand enough to hold trillions of unique galaxies without ever crowding them out. It explains that our home galaxy possesses ample room to move, room to evolve, and room to orbit its cosmic peers without triggering constant, destructive head-on collisions. It demonstrates that the cosmos is defined not just by the matter that is present, but by the magnificent spaces separating those things. And in a beautiful twist, it teaches us something profound about ourselves as well. We naturally focus our attention on what is visibly present, on the stars, the planets, and the bright galaxies. But occasionally, the empty spaces in between are just as vital, defining the overall context and granting true significance to everything that exists. Therefore, the gap between galaxies, though monumentally vast and seemingly vacant, is an essential thread in the fabric of the universe. It is quietly filled with diffuse gas, lonely rogue stars, background radiation, and invisible dark matter. It is organized by grand filaments and perpetually shaped by the laws of gravity. It serves as a magnificent stage upon which all galaxies travel, the boundless ocean across which they drift. And while it may appear to be a total vacuum, it is actually a quiet, subtle, and essential presence. From this vantage point, we can continue our journey outward to witness how these massive gaps give way to colossal clusters, how galaxies assemble into even grander architectures, and how the universe itself is systematically arranged. For the time being, however, the thought remains steady and perfectly clear. Between galaxies lies not a state of nothingness, but a vast space that holds the entire cosmos together, a beautiful silence resting between two songs. When we were analysing the gaps between galaxies, the structural image that emerged was one of distinct islands, isolated by massive oceans of emptiness. But the moment you choose to step back far enough to view not just 2 or 3 systems, but hundreds of thousands of them, an entirely new structural pattern reveals itself to you. The cosmic islands are not tossed blindly or scattered at random throughout space. They actively gather, they cluster, and they form structures that are vastly grander than themselves. The Milky Way, Andromeda, and their small satellite retinue belong to the family known as the local group. That group, in turn, is merely a single thread in a grander structural pattern linked together by the invisible gravitational pull of dark matter. These massive architectural links are what astronomers call clusters and superclusters, the great gravitational highways along which galaxies travel over eons of time. To describe their dimensions requires us to shift our cognitive scale once more, moving from millions of light years to hundreds of millions, and watching the cosmic web emerge in its full majestic glory. A cluster of galaxies is exactly what the word implies, a highly concentrated assembly of systems bound securely together by gravity, packed far more densely than the loose, sparse arrangement of our local group. Within a typical cluster, dozens, hundreds, or even thousands of independent galaxies orbit around a shared center of mass, swimming together in a massive pool of superheated gas and dark matter. One of the closest and most thoroughly studied examples is the famous Virgo cluster, located roughly 65 million light-years away from our position. This cluster hosts more than 1,000 individual galaxies, boasting elegant spirals like our Milky Way, colossal ellipticals packing trillions of stars, and tiny dwarfs scattered throughout the entire domain. If you could look at the Virgo cluster through an instrument large enough to capture its complete expanse, the visual sight would be absolutely breathtaking. Galaxies would appear scattered like precious jewels across the heavens, so intensely numerous that the sky would look crowded even across such mind-boggling distances. Furthermore, clusters are not merely collections of distinct galaxies. They also serve as massive reservoirs for hot, diffuse gas that has been superheated to tens of millions of degrees, glowing brightly in the X-ray spectrum. This intra-cluster medium actually contains substantially more ordinary mass than all the visible galaxies combined, a stark reminder that what our human eyes see in visible light is only a tiny fraction of the total story. Galaxies plough through this dense, hot medium exactly like fish swimming through water. While their internal stars remain completely unaffected by the journey, their vital gas reservoirs are systematically stripped away and reshaped by the hydrodynamics of the interaction. Invisible dark matter also plays a dominant role here, its immense gravity binding the entire cluster together and creating a gravitational well so deep that individual galaxies can almost never escape its grip. In this precise sense, a cluster behaves far more like a complex ecosystem than a simple collection, with galaxies, superheated gas, and dark matter all interacting in intricate ways. These massive clusters themselves gather into even grander structural arrangements known to science as superclusters. A supercluster represents a colossal region of space where independent clusters and groups are structurally connected, reaching across hundreds of millions of light years. The Virgo cluster serves as the central hub of the Virgo supercluster, a sprawling arrangement that includes our own local group as a tiny member sitting on its remote outskirts. For several decades, astronomers utilized the Virgo supercluster as our official cosmic address, explaining that we lived in the Milky Way, within the local group, on the quiet outskirts of Virgo. But as our architectural maps of the wider universe grew increasingly detailed, it became clear that even the massive Virgo supercluster was merely a single component of something vastly grander still. In the year 2014, a team of astronomers proposed a revolutionary new map of our cosmic landscape, naming this grander master structure Laniakea Kea, which translates to immense heaven in the Hawaiian language. Laniakea Kea encompasses not only the Virgo supercluster, but many neighbouring clusters as well, stretching across a staggering 500 million light-years and housing roughly 100,000 individual galaxies. Our local group sits right on one of its outermost frontiers, drifting slowly along gravitational currents toward the central region where the Great Attractor, a massive, dense concentration of galaxies and matter, quietly pulls everything inward. This discovery fundamentally reframed our place in the cosmos once again. We are not only members of the Milky Way, the local group, and the Virgo supercluster, but we are official citizens of Laniakea Kea, a supercluster so monumentally vast that the word immense starts to sound incredibly small beside it. The concept of gravitational flow is highly critical to grasp here. Galaxies do not sit static or motionless inside these clusters and superclusters. They travel along precise pathways explicitly carved out by the layout of surrounding mass, moving exactly like rivers flowing downhill. These trajectories form what cosmologists refer to as cosmic highways. the invisible structural routes along which galaxies drift over the course of billions of years. These highways are sculpted by gravity, channeled by dark matter, and filled with a thin presence of diffuse gas. They are obviously not roads in the conventional sense, but they perform the exact same function, systematically connecting one cosmic region to another, guiding long-term motion and dictating macrostructure. When astronomers map out these grand flows, they witness a universe that is not a chaotic scattering of points, but a beautiful web of connections, where every single strand leads to a central hub, and each hub is linked to others. The entire integrated pattern stretches out across billions of light years. To grasp the scale of this structure, imagine mentally shrinking the entire Milky Way down to the microscopic size of a single grain of sand. On that specific scale, our local group would manifest as a small pebble, the Virgo cluster would appear as a large stone, and the Laniakea supercluster would be the size of an entire continent. Now, visualize that continent floating inside a boundless ocean alongside countless others, with each one representing a unique supercluster featuring its own independent rivers of galaxies flowing inward. Viewed on these grand scales, the universe looks less like a simple void with scattered islands, and more like a massive, interconnected network, a magnificent cosmic web where vast filaments connect bright nodes, and immense voids stretch out between them like soap bubbles. Clusters, superclusters, and cosmic highways represent the fundamental architecture of this web, the grand scaffolding upon which all the galaxies are hung. The existence of these grand structural patterns was far from obvious to humanity until relatively recently. In the middle of the 20th century, astronomers still held the belief that galaxies were mostly isolated anomalies, viewing dense clusters as rare exceptions to the rule. It was only through the advent of massive digital surveys mapping out the exact redshifts of thousands of galaxies that these larger patterns finally came into view. The very first three-dimensional maps revealed colossal walls and filaments, structures so staggeringly vast that they challenged our core assumptions about how matter could be distributed through space. The famous Sloan Great Wall, discovered in the year 2003, reaches across a staggering 1.3 billion light-years. The Hercules Corona Borealis Great Wall, documented in 2013, is grander still, holding the title of one of the absolute largest known structures in the entire universe. These discoveries proved that clusters and superclusters are not the peak of the cosmic hierarchy. They are merely components of a grander pattern woven directly into the cosmic web itself. And yet, even with these colossal dimensions, the architecture remains delicate. The filaments are thin, the clusters are scattered, and the empty voids remain immense. The vast majority of the universe is still completely empty, but the sectors that are filled reveal a structural blueprint that perfectly repeats across scales. Individual galaxies gather into groups, groups organize into clusters, clusters link into superclusters, superclusters weave into filaments, and filaments combine to form colossal walls. It is a hierarchy that extends upward as far as our instruments can see, but it does not extend forever. On the largest scales imaginable, looking beyond a few billion light years, the universe starts to look smooth, and the distinct features of the cosmic web fade into uniformity. At that macro level, massive clusters and superclusters are merely tiny ripples resting on the surface of something infinitely more vast. For those of us living deep inside the Milky Way, these cosmic clusters and highways are impossible to feel directly. Our local night sky displays only the nearest stars of our own galaxy, and while a telescope can resolve independent galaxies, the macro patterns connecting them are far too large to ever be processed by the naked eye. It requires advanced data maps, deep surveys, and supercomputer simulations to reveal the cosmic web in its fullness. Yet, once you understand it is there, the universe feels entirely different. The stars overhead are no longer random points of light. They are bound to a galaxy. That galaxy belongs to a group. That group is part of a cluster. That cluster is woven into a supercluster, and all of them are connected by highways of gravity, flowing slowly and inevitably through cosmic time. This structural realization fundamentally transforms how we view motion. When you walk down a city street, you are fully aware of where the pavement leads. When you drive along an interstate, you understand that it bridges one metropolis to another. In that identical fashion, galaxies cruise along cosmic highways, not wandering aimlessly, but navigating tracks carved out by massive centres of weight. Our own local group is currently migrating toward the Virgo cluster. Virgo itself is travelling within the boundaries of Laniakea, and Laniakea is structurally linked to adjacent superclusters on timelines measured in billions of years. These grand trajectories dictate the long-term future of the universe, orchestrating close encounters, mergers, and the birth of completely new systems. Viewing the universe through this lens reveals it as an active environment, bustling with movement, with every single galaxy swept up in a macro current. It is well worth taking a quiet moment to contemplate what it truly means to be a resident of an entity as monumentally large as Laniakea. The Hawaiian phrase meaning immense heaven feels completely appropriate because its physical scale dwarfs anything our minds can accurately visualize. It spans 500 million light years from side to side, hosting roughly 100,000 independent galaxies within its domain, with structural filaments flowing like rivers, clusters functioning like massive cities, and groups acting like quiet villages, all connected and migrating toward the same centers of gravity. And we, living out our lives on this tiny planet, orbiting a perfectly ordinary star, tucked into a spiral arm of the Milky Way, are a physical part of that grand network, not separate from it, not isolated onlookers, but locked deep within its borders, travelling right along with its currents. The spatial scale is staggeringly vast, yet the connection is deeply intimate. The supercluster is not a far-off alien object, it is right here, and we are residing inside its architecture. It is beautiful to linger on this mental image of clusters, superclusters, and cosmic highways stretching out endlessly across space. These are the grand landmarks that dictate our neighbourhood layout on the largest imaginable scales. They represent the avenues upon which galaxies travel, the urban centres where cosmic systems assemble, and the sprawling continents of our cosmological landscape. They stand as proof that the universe is not a chaotic mess, but an organised pattern, beautifully structured rather than random. And they remind us that even the grandest architectures our imaginations can grasp are merely smaller components of a reality that is grander still. When we look at these colossal clusters, superclusters, and filaments reaching across hundreds of millions of light years, it is exceptionally easy to marvel at their sheer size. But another critical inquiry quickly surfaces, one that is as practical as it is awe-inspiring. How do astronomers manage to measure something so incredibly vast? How can they assign definitive metrics to distances so large that light itself requires millions or billions of years just to cross from one side to the other? How can we state with absolute certainty that the Milky Way spans 100,000 light years from edge to edge, that Andromeda is situated 2 million light years away, or that the Virgo cluster reaches across tens of millions? These are not geographic paths anyone can physically travel. They are not parameters that can be audited with a physical ruler or compared to anything inside our human experience. And yet, despite these obstacles, scientists have engineered brilliant ways to do exactly that. Tonight, let us walk slowly through those ingenious techniques step by step and discover how the seemingly immeasurable becomes entirely measurable. The most elementary asset at our disposal is starlight itself. Every star, every galaxy, and every energetic explosion or subtle flicker across the cosmos radiates light, and that light serves as a deep repository of information. It travels outward in all directions across the vacuum of space, fading in intensity with distance, but never erasing the unique chemical signature of its origin. Astronomers treat this light as a reliable cosmic courier, decoding its underlying patterns to discover exactly where a celestial object is situated, how rapidly it is travelling, and even what elements comprise its structure. But converting that raw data into a reliable calculation of distance requires an extraordinary amount of human creativity. This is because there is no shortcut or direct way to measure how far away a cosmic object sits simply by looking at it. To overcome this hurdle, researchers deploy an integrated network of methodologies known to science as the cosmic distance ladder, with each individual rung relying on a distinct physical technique. Every single step builds securely on the foundation established by the previous one, to reach increasingly grander scales of distance. The premier rung of this foundational ladder is parallax. This technique measures the apparent shift in location of a nearby star against a static background of highly distant objects caused explicitly by a change in the observer's physical viewpoint. You can demonstrate this geometry yourself by holding your index finger directly in front of your face and looking at it with only your left eye, and then switching to your right eye. Your finger will appear to physically jump relative to the background objects in the room. Astronomers utilize this exact line of sight principle by tracking nearby stars at opposite times of the calendar year, when the Earth has traveled to opposite sides of its physical orbit around the Sun. The closer a target star sits to our solar system, the grander its apparent shift will be against the background. By carefully calculating this microscopic geometric angle, scientists can mathematically deduce the star's exact distance. Parallax represents the most direct and trustworthy calculation available, but it can only evaluate stars located within a few thousand light years of our position. This is because beyond that threshold, the shifting geometric angles become far too small for our instruments to record. However, with the deployment of cutting-edge space observatories like the Gaia spacecraft, parallax has been successfully computed for over 1 billion individual suns, yielding a highly accurate map of our local galactic architecture. When mapping regions beyond the reach of pure parallax, astronomers must rely on what are known as standard candles. These represent specific cosmic objects whose true absolute brightness is known, allowing their distance to be calculated by comparing that absolute value to how bright they appear to our telescopes. One of the most critical standard candles in modern astrophysics is a distinct classification of star known as a Cepheid variable. These suns pulse in brightness with a highly predictable clockwork rhythm, and the exact duration of their pulse is directly tied to their true absolute luminosity. By carefully tracking the rhythm of the pulse, astronomers unlock exactly how much energy the star is truly emitting. By weighing that absolute metric against how dim the star looks from our vantage point on Earth, they can compute precisely how much distance the light had to travel to reach us. Cepheid variables allow us to cross the intergalactic gap, measuring distances far beyond our own borders and into neighbouring galaxies. Another monumental standard candle is the Type 1a supernova, a cataclysmic explosion involving a white dwarf star that always peaks with roughly the identical absolute brightness. Because these stellar detonations are so blindingly luminous, visible across billions of light years of space, they are absolutely vital for evaluating distance on the grandest cosmological scales. By carefully analysing their light curves and comparing them to the known absolute standard, astronomers can plot far-off galaxies onto our three-dimensional map of the universe with a remarkable accuracy. It was the meticulous study of these specific supernovas in the late 1990s that revealed the accelerating expansion of space, a groundbreaking discovery that directly introduced the concept of dark energy to modern science. In this sense, our methods of measurement do more than just show us where objects are located. They reveal exactly how the universe itself behaves. Spectroscopy provides another powerful tool for our arsenal. When starlight travels across the void of space, it carries the unique atomic fingerprint of the specific elements that emitted or absorbed it along the way. By dispersing this light into its component spectrum, astronomers can read these elemental barcodes to learn about the nature of the source, but they can simultaneously evaluate another critical factor: redshift. As the fabric of the universe expands, the light travelling through it is physically stretched out, systematically shifting toward the longer redder end of the electromagnetic spectrum. The grander the recorded redshift, the further away that galaxy sits from us. This direct relationship, originally uncovered by Edwin Hubble, stands today as one of the most vital methodologies for calculating cosmological distance. By calibrating recorded redshifts against the metrics secured from other independent techniques, astronomers can use it to confidently map out galaxies situated billions of light years away. It is certainly not a perfect system, as localized cosmic movements can introduce statistical noise into the data, but on the macro scales, it beautifully charts the architecture of the cosmic web. Gravitational lensing offers yet another ingenious method of measurement. When light radiating from a highly distant background object passes close to a massive foreground galaxy or cluster, its trajectory is physically bent and distorted by the intense gravitational field. This creates magnified arcs, distortions, or even multiple cloned images of the background source. By carefully analysing the shape, magnification, and geometry of this lensing effect, astronomers can infer the exact mass of the foreground lens and calculate the distance to the background source. This technique does double duty. It measures vast distances while simultaneously charting the distribution of dark matter, which reveals its presence through gravity even though it can never be seen directly. In this elegant manner, measurement becomes a way of uncovering the invisible infrastructure of the universe. In certain unique cases, time itself functions as a cosmic yardstick. Pulsars, the hyperdense, rapidly spinning remnants of collapsed giant stars, emit concentrated beams of radiation with absolute clockwork regularity. By precisely timing these incoming pulses, astronomers can log microscopic variations caused by spatial distance and motion. Similarly, quasars, the brilliant hearts of active galaxies powered by supermassive black holes, flicker with a specific variability that can be utilized as a reliable cosmic benchmark. While these methods are highly complex and specialized, they showcase the immense creativity astronomers must demonstrate to convert the seemingly immeasurable into something that can be clearly described. The cosmic distance ladder is identified as a ladder for a very specific reason. Every single rung supports the one sitting above it. Direct parallax measurements calibrate our calculations for Cepheid variables. Cepheid variables are then used to calibrate the absolute brightness of supernovas. Supernovas, in turn, calibrate our redshift calculations, and redshift extends our scientific reach across billions of light years to the very edge of the observable universe. Every step builds on the absolute certainty of the rung below it, forging an unbroken chain of measurement that spans from our immediate stellar backyard out into the deep cosmos. The system is certainly not without flaws, as mathematical errors can compound across layers, and intense debates persist within the scientific community regarding the precise values of certain far-off distances. But the macro framework is robust enough to build highly reliable maps of the universe, allowing us to state with confidence exactly how wide the Milky Way spans, how far Andromeda sits across the gulf, and how vast the universe itself must be. It is well worth reflecting on how truly extraordinary this achievement is. From our position on a small planet orbiting an ordinary star, we have engineered ways to calculate the distances to structures so unfathomably far away that their light has been travelling across the vacuum for billions of years. We have constructed scientific instruments sensitive enough to resolve angles no wider than the thickness of a human hair, viewed from across an entire city. We have identified unique stars whose internal pulses function as reliable yardsticks, tracked stellar detonations whose light can bridge cosmic epochs, and evaluated redshifts that expose the expansion of space itself. To calculate the immeasurable requires us to stretch human ingenuity and imagination to their absolute limits. And yet, we have successfully done it, creating a map of the universe that is simultaneously deeply humbling and intensely empowering. This knowledge fundamentally alters how we perceive ourselves. Understanding that Andromeda sits 2 million light years away is far more than just memorizing a dry metric. It is realizing that the faint smudge of light hanging in our night sky left its source long before the first humans walked the Earth. Realizing that the Virgo cluster is situated 65 million light years away means understanding that its incoming light began its journey when dinosaurs still dominated this planet. Knowing that the cosmic microwave background dates back 13.8 billion years means recognizing that we are directly gazing at the fading afterglow of the universe's birth. Measurement masterfully converts distant light into a concrete chronological timeline, connecting our eyes to events across the span of cosmic history. These vast numbers are far more than quantities. They are markers of time and place, anchoring us in the story of the cosmos. At the exact same time, it is vital to remember that every measurement we log carries a margin of uncertainty. The universe is monumentally vast, and our tools, though brilliant, have physical limits. Distances are constantly refined as our telescopes improve, deep surveys expand, and different methodologies are cross-checked against one another. The specific numbers shift slightly over time, and our cosmic maps become increasingly clear, but the overarching realization remains completely unchanged. Galaxies are vast, the universe is grander still, and our place within its architecture is both small and extraordinary. The journey of measurement is an ongoing process, a continuous effort to sharpen our view of a reality that will always remain partly beyond our grasp. As we choose to sit with this realization, the phrase "measuring the immeasurable" ceases to sound like a paradox. The universe completely eclipses any human scale, but it can never eclipse human curiosity. We cannot step outside our borders and stretch a tape measure across galactic voids, but we can utilize light, motion, and gravity as our tools. We can carefully climb the cosmic distance ladder, rung by rung, until our vision reaches the furthest objects in existence. And although there will always be distant horizons beyond which our instruments cannot measure, the dedicated act of trying brings the universe into sharp focus one step at a time. From the subtle geometric shifting of nearby stars to the redshift of galaxies located billions of light years away, we have successfully converted the immeasurable into something describable, and in doing so, we have granted ourselves a way to comprehend scale, to compare the Milky Way to the universe, and to see not only how big things are, but also how connected they are. When we contemplate how astronomers measure the cosmos, what emerges is not just a set of numbers, but a way of stretching our imagination to meet the universe halfway. With parallax, Cepheids, supernovas, and redshifts, we climb rung after rung of the cosmic distance ladder until finally we arrive at the broadest scale we can reach. That scale is what we call the observable universe. The phrase itself invites curiosity. It is not simply the universe, but the observable universe, suggesting both an expanse and a limit, a horizon beyond which our instruments cannot see. To glimpse this horizon is to look as far back in time as the laws of physics will allow, to the very edge of light itself. The observable universe is defined by distance in time, not in space alone. Light travels at a finite speed. That speed is unimaginably fast compared to our everyday world, nearly 300,000 kilometers per second, but it is not infinite. When you look at the moon, you see it as it was about a second ago. When you look at the sun, you see it as it was 8 minutes ago. When you look at Andromeda, you see it as it was 2 million years ago. Every gaze outward is also a gaze backward. At the farthest limit, the light we see has been travelling since the universe was very young. That light comes to us as the cosmic microwave background, radiation from when the cosmos was just 380,000 years old. Beyond that point, the universe was too hot and dense for light to travel freely, so the horizon begins there. To look farther is not possible because there is no light older than that to reach us. This horizon defines the observable universe. It is not a wall, not an edge in the ordinary sense, but a limit created by time. Light has had only 13.8 billion years to travel since the Big Bang. But because the universe has been expanding during that time, the distance to the farthest objects we can observe is greater than 13.8 billion light years. In fact, those objects are now about 46 billion light years away. That means the diameter of the observable universe is about 93 billion light years across. This number is almost incomprehensible, so large that even when spoken slowly, it resists settling in the mind. 93 billion light years, a horizon defined by time and expansion, containing everything we can possibly observe. Next, we will step up to this horizon and look directly at what it contains. what lies inside this observable bubble is absolutely staggering. Estimates suggest there are about 2 trillion galaxies inside it, each with hundreds of billions of stars. That means the total number of stars is around 10 to the 24th power, a number so large it is difficult to say aloud without it dissolving into abstraction. That is a 1 followed by 24 zeros. If each star were a grain of sand, they would fill every beach on Earth many times over. And yet even that number may be conservative, because faint galaxies too dim for current telescopes may number even more. The observable universe is not just vast, it is overflowing with light. To glimpse it is not to see it all at once, of course. No telescope can take in the whole observable universe. Instead, astronomers build maps piece by piece, surveying patches of sky and stitching them together into a panorama. The Hubble Ultra Deep Field, for example, is one of the most famous glimpses. Pointing the Hubble Space Telescope at a tiny patch of sky, no larger than a grain of sand, held at arm's length, astronomers collected light over many days. The result was an image filled with thousands of galaxies, each a swirl or smear of light. Multiply that patch across the sky, and you reach billions. The James Webb Space Telescope has extended this vision even farther, peering into earlier epochs, finding galaxies that existed less than 1 billion years after the Big Bang. These glimpses are like peeking through a keyhole and seeing an entire city beyond, only to realize that the city stretches farther than you can imagine. The observable universe is not uniform though. It is structured, shaped by the same cosmic web we spoke of before. Galaxies cluster into filaments. Filaments weave into walls, and between them lie vast voids. The largest of these voids span hundreds of millions of light years, nearly empty, while the densest clusters blaze with galaxies packed tightly together. When astronomers map these structures, they see a pattern that looks almost biological, like neurons in a brain or filaments in tissue. It is a reminder that the universe on its largest scales has a kind of coherence, a pattern that emerges from gravity pulling matter into threads and knots. One of the most humbling aspects of the observable universe is that it is not the whole universe. It is simply the part we can see. Beyond the horizon, the universe almost certainly continues. There is no reason to think that space ends abruptly at 46 billion light years. It likely extends far beyond, perhaps infinitely, though we cannot observe it. This distinction is subtle but important. The observable universe is not a container, not the whole story, but a bubble defined by the speed of light and the age of the cosmos. To glimpse it is to glimpse a boundary, not of the universe itself, but of our vision. This limitation makes the universe feel even more mysterious. We live inside a bubble of light, and everything we know about the cosmos is contained within it. Beyond the bubble, we cannot see, though we can imagine. Perhaps the patterns of galaxies continue. Perhaps they change. Perhaps there are regions so different from ours that they would challenge our understanding of physics. Or perhaps everything looks much the same, repeating endlessly. We cannot know. The observable universe is as much about what lies beyond our reach as it is about what lies within it. It is striking to think how recent this knowledge is. Barely a century ago, astronomers were still debating whether galaxies outside the Milky Way even existed. The observable universe, as we now describe it, was unimaginable then. And yet in that short time, we have gone from thinking our galaxy was the whole cosmos, to realizing that it is just one among trillions inside a bubble 93 billion light years across. This expansion of awareness is one of the most profound shifts in human thought, changing not only our scientific models, but our place in the story of existence. To glimpse the observable universe is to glimpse our own smallness, but also our capacity to comprehend. From Earth, the observable universe is centered on us simply because we see outward in all directions. But every observer anywhere has their own observable universe centered on them. Someone in a galaxy billions of light years away would also see a bubble 93 billion light years across, but the contents would be different. This fact reinforces that the observable universe is not a physical edge but a horizon, one that depends on where you stand. It is like standing in the middle of a fog. Each person sees a circle around them, but the fog itself stretches beyond all of them. Our horizon is ours, but it is not the limit of reality. To glimpse this horizon is not only to marvel at its size, but also to feel a kind of quiet comfort. The observable universe contains everything we will ever know. All the galaxies, all the stars, all the light. It is a complete picture, even if it is not the whole story. To live inside it is to live inside a bubble of knowledge, one that expands slowly as time passes, because with each year, light from slightly farther away reaches us. The observable universe is growing, not because space itself is expanding into something, but because more of it becomes visible as light travels. Every second, more of the cosmos enters our sight, and more of the past arrives at our doorstep. This thought makes the observable universe not just a limit, but a process. It is a horizon that changes, a boundary that recedes with time. It reminds us that we live not in a static cosmos, but in a dynamic one, where new discoveries are always possible. To glimpse it today is to see one picture. To glimpse it 1,000,000 years from now would be to see more, to add new galaxies to the map, to extend the bubble outward. The observable universe is not fixed. It is a horizon always in motion, expanding with our view. So when we say we glimpse the observable universe, what we really mean is that we glimpse the farthest light, the faintest signals, the oldest echoes. We see galaxies billions of light years away, their light arriving across time. We see the cosmic microwave background, the afterglow of creation itself. We see structure on the largest scales, filaments and walls spanning hundreds of millions of light years. We see a bubble 93 billion light years across, filled with 2 trillion galaxies, and beyond it, we imagine more. That is the glimpse, not everything, but enough to feel the immensity. Enough to know that our galaxy is small compared to the whole. Enough to place ourselves in a cosmos that is larger than words can contain. The observable universe is not the final answer, but it is the farthest view we can take. To glimpse it is to stand at the edge of knowledge, looking out into a vastness that is both known and unknown, measurable and mysterious, finite in sight, but perhaps infinite in reality. When we take in the picture of the observable universe with its horizon stretching 93 billion light years across and its contents numbering in the trillions of galaxies, the natural question that follows is how our own Milky Way compares to all of this. We know it is large in its own right, 100,000 light years across with hundreds of billions of stars. We know it is a barred spiral with graceful arms and a central bulge anchored by a supermassive black hole. We know it contains dark matter, gas, dust, clusters, and streams. And yet, when placed against the backdrop of the whole observable universe, the Milky Way is not even a giant. It is an ordinary spiral, one among trillions, occupying a fraction of the cosmic expanse. To compare the Milky Way to the universe is to compare a single grain to a desert, a single wave to the ocean. And yet to do so carefully is to give scale to both, to see how our home fits into the whole. The first step is to think about relative size. The Milky Way is about 100,000 light years across. The observable universe is 93 billion light years across. To put those numbers together is to place one next to the other. 100,000 compared to 93 billion. That means the observable universe is about 900,000 times larger than the Milky Way in diameter. In volume, the difference is even more staggering. If you cube the ratio, the observable universe is about 10 to the power of 18 times larger in volume than the Milky Way. That is a billion times. If the Milky Way were reduced to the size of a coin, the observable universe would be the size of a continent. If the Milky Way were a single drop of water, the observable universe would be an ocean stretching beyond the horizon. The next step is to compare populations. The Milky Way contains between 200 and 400 billion stars. That number is immense on its own, enough that every human alive could have dozens of suns to themselves. But the observable universe contains about 2 trillion galaxies. If each one has an average of 100 billion stars, the total number of stars is around 10 to the 24th power. That is a septillion, a 1 with 24 zeros. Compared to this, the Milky Way's stars are a drop in a cosmic bucket, a few hundred billion out of a septillion. To say it another way, if every star in the Milky Way were a grain of rice, it would fill a silo. But if every star in the observable universe were a grain of rice, it would fill Earth's oceans many times over. The numbers multiply until they become overwhelming, and yet they are precise enough to give us perspective. The Milky Way is also not exceptional in type. It is a barred spiral, mid-sized, with an ordinary supermassive black hole at its centre. Galaxies come in many forms: ellipticals containing trillions of stars, dwarf irregulars with only millions, spirals with graceful arms, and lenticulars that are somewhere in between. The Milky Way falls in the middle of this spectrum. Andromeda, our nearest large neighbour, is larger. Ellipticals, like M87 in the Virgo cluster, are much larger still, containing several trillion stars. Dwarfs like the Magellanic Clouds are smaller against the universe. The Milky Way is typical, not the largest, not the smallest, not unusual in shape or features. To us it feels immense and unique, but in the larger context, it is an average citizen of the cosmos, one spiral among countless others. This ordinariness is, in a way, profound. If the Milky Way were unusual, it might suggest that our place in the universe is special, a rare exception. But the fact that it is typical suggests that the universe is filled with galaxies like ours, each with stars, planets, and perhaps life. It suggests that what we experience here may not be unique, that somewhere in another spiral there may be suns and worlds not unlike our own. To compare the Milky Way to the universe is not to diminish it, but to see it as part of a larger pattern, a thread woven into a vast tapestry. The beauty lies not in its uniqueness, but in its belonging. To give more tangible comparisons, astronomers often use scale analogies. If the Milky Way were shrunk to the size of a city, the observable universe would be larger than the Earth itself. If the Milky Way were a house, the universe would be a planet. If the Milky Way were a grain of sand, the universe would be a beach stretching for thousands of kilometers. Each analogy helps, but none can fully capture the immensity because our minds are not built to handle such scales. We can only approximate, gesture, hint at the difference, and yet even a hint is enough to feel the smallness of our galaxy and the vastness of the universe. The comparison also brings time into focus. The Milky Way is about 13 billion years old, nearly as old as the universe itself. It formed not long after the first galaxies, growing through mergers and accretion. Its stars trace back to nearly the beginning. In this sense, the Milky Way is ancient, but the universe is older still. The first galaxies formed when the universe was only a few 100 million years old. Since then, galaxies have grown, collided, evolved, and changed. The Milky Way is part of that history, a product of cosmic evolution, but not the whole story. To compare the two is to see the Milky Way as a chapter in a much larger book, one of trillions of chapters, each with its own plot, each contributing to the narrative of the universe. Another perspective comes from motion. The Milky Way orbits within the local group, drifting toward Andromeda. The local group itself is moving toward the Virgo cluster. Virgo is moving within Laniakea. All of these motions are part of the flow of the cosmic web, currents of gravity that shape the universe. Compared to these flows, the Milky Way is a single leaf in a river, carried along by forces much larger than itself. The observable universe is the river system stretching across the landscape. The comparison shows not only a difference in size, but a difference in context. The Milky Way is part of something larger, moving within it, shaped by it, inseparable from it. Next, we will step off these moving highways and trace the final edge where the observable ends and the unseeable begins. When we take that final step out to the very edge of the observable universe, we find ourselves standing before a boundary that is fundamentally different from any other frontier we have crossed. The edge of a country is defined by law, the edge of a planet is marked by its surface, the edge of a galaxy is dictated by the fade of its gravity. But the edge of the observable universe is a barrier constructed out of time itself. It is a shifting horizon established by the finite speed of light and the absolute age of the cosmos, marking the exact boundary between what is knowable to us and what must remain forever hidden in the deep dark. Tonight, as we bring our journey to its quiet conclusion, let us stand at this final cosmic horizon and contemplate what it truly means to look out at the very edge of the seeable, allowing our minds to settle into the ultimate vastness of space. The concept of the cosmological horizon is deeply tied to the fact that light requires time to travel across space. Because the universe is approximately 13.8 billion years old, the absolute farthest light that could theoretically reach our instruments today is light that began its journey 13.8 billion years ago, right at the dawn of creation. If the universe were perfectly static and unchanging, this would mean our observable bubble would have a radius of exactly 13.8 billion light years. But our universe is not static. It has been actively expanding since the moment of the Big Bang. While the ancient light from the most distant regions was travelling toward us, the space behind it was stretching out, pushing the physical sources of that light much further away. Today, the galaxies that emitted that earliest radiation have been carried out to a distance of roughly 46 billion light years from Earth. This means the total diameter of our seeable bubble stretches across a mind-boggling 93 billion light years. Absolutely everything we can ever see, detect, or interact with is locked inside this 93 billion light year sphere. But what lies beyond that 93 billion light year horizon? This is one of the most profound mysteries in all of modern science. The short answer is that we simply do not know with absolute certainty, because no signal or piece of information can ever cross the horizon to reach us. However, the laws of physics and our current cosmological models provide highly reliable clues. The universe does not feature a physical wall or a literal drop-off at the edge of our vision. If you were somehow transported to a galaxy sitting right on the edge of our observable bubble, you would not look out into a blank void or a sudden nothingness. Your local view of the cosmos would look almost identical to the view we have from Earth. You would see yourself sitting right in the center of your own unique observable bubble, spanning 93 billion light years across, filled with trillions of galaxies, clusters, and filaments woven into a familiar cosmic web. The horizon is not a characteristic of space itself. It is a characteristic of our specific vantage point. It functions exactly like the horizon you see when standing on the surface of the ocean. The water continues smoothly beyond the curve of the Earth, but your eyes can only see as far as the geometry of the sphere allows. Because space continues beyond our vision, the true, total universe is almost certainly vastly larger than the small bubble we can observe. Many cosmologists believe that if the universe is finite, it must curve back on itself like a colossal sphere, with a total size that is hundreds or even thousands of times larger than our seeable portion. Other models suggest that space is perfectly flat and extends outward infinitely, meaning it holds an infinite number of galaxies, an infinite number of stars, and an infinite number of worlds stretching out forever through the dark. In an infinite universe, the 93 billion light years we can map is reduced to a statistical zero, a single drop of water in an ocean that has no shoreline. Whether the total universe is infinitely vast or merely unfathomably large, the realization remains completely unchanged. The observable universe is just a microscopic patch of a reality that stretches far beyond our ultimate capacity to see. This boundary between the seeable and the unseeable is not static. It is in constant dynamic motion due to a mysterious force known to science as dark energy. Discovered in the late 1990s through the careful study of distant supernovas, dark energy acts as a cosmic repulsion, causing the expansion of space to accelerate over time. This acceleration introduces a poignant twist to our cosmic story. As space stretches faster and faster, Far-off galaxies are being carried away from us at speeds that will eventually exceed the speed of light. This does not violate Einstein's theory of relativity, because the galaxies are not moving through space at that speed. Rather, the fabric of space itself is stretching between them. The practical result of this acceleration is that the galaxies on the outer edge of our vision are permanently slipping across our cosmic horizon. Once a galaxy crosses that threshold, the light it emits can never catch up to the expanding space separating us, meaning it is forever lost to our sight. We are living in a unique epoch of cosmic history, where the wider universe is still visible to us. In the deep future, trillions of years from now, the expansion will have carried all neighbouring clusters so far away that the night sky from Earth will look completely dark, revealing no other galaxies at all. This realization infuses our current view of the cosmos with a beautiful sense of urgency and appreciation. The trillions of galaxies we can map tonight, the great filaments of Laniakea, the majestic smudge of Andromeda, and the hundreds of billions of stars inside our own Milky Way are gifts of our specific placement in time. We are privileged to live in a universe that is still open to our exploration, a cosmos whose history is still written clearly in the incoming starlight. To compare our home galaxy to this grand reality is to balance on a tightrope between complete insignificance and extraordinary significance. In terms of pure scale, the Milky Way is a microscopic point, an ordinary spiral completely lost inside a 93 billion light-year bubble that itself is just a fraction of the total universe. If humanity were to vanish tomorrow, the cosmic web would continue to flow, stars would continue to ignite inside distant nebulae, and supermassive black holes would continue to anchor their galaxies entirely uninterrupted. We are not the centre of this architecture, and the universe does not require our presence to maintain its majestic balance. And yet, there is another way to view this comparison. The universe is monumentally vast, but it is also completely silent and unthinking. The stars do not know they are burning. The galaxies do not appreciate the elegant geometry of their spiral arms. The cosmic highways do not marvel at the rivers of light travelling along their pathways. It requires a conscious mind, a thinking observer, to convert that raw matter and energy into meaning. From our tiny launch pad on Earth, utilizing nothing more than light, gravity, and human ingenuity, we have successfully climbed the cosmic distance ladder. We have mapped out the shape of our galactic home, calculated the distance to our neighbours, traced the outlines of superclusters, and looked directly at the fading afterglow of the universe's birth. We are the mechanism through which the cosmos has successfully achieved self-awareness. The atoms that comprise your body were forged billions of years ago inside the hearts of dying suns, and tonight those very same atoms are looking back upward at the heavens, asking questions about the scale of the system that created them. You are not a separate observer looking at the universe from the outside. You are a piece of the universe that has developed the capacity to think, to feel, and to wonder. As we bring our long cosmic journey back to where it originally began, let your thoughts drift back down to the solid earth beneath you. Picture yourself once more standing outside beneath a crisp, clear night sky, listening to the deep silence of the dark and watching the gentle flickering of the stars. The vast scales we have analysed tonight, the 100,000 light-years of the Milky Way, the millions of light-years of the local group, the hundreds of millions of light-years of Laniakea, and the 93 billion light-years of the observable universe, are no longer just intimidating numbers on a page. They are the structural layout of your home. The night sky is transformed from a random collection of lights into the intimate inside view of a magnificent spiral system nested inside a community of neighbours, connected by highways of gravity to a vast web of light that stretches out to the ultimate horizon of time. The infinite stretches out beyond us, but it also holds us safely within its framework. To rest beneath its vastness is not to feel overwhelmed, but to settle into a deep, profound sense of calm. The anxieties of a single day or the pressures of our local lives shrink to nothing when framed against a backdrop of trillions of galaxies drifting peacefully through cosmic time. This perspective does not make your life unimportant. It simply grants you ample room to breathe. A quiet reminder that you belong to a reality that is grand enough to hold absolutely everything without ever losing track of the parts. The universe continues above us tonight, vast, steady, and beautifully ordered, carrying on its long orbits whether we are actively watching or not. The galaxies remain securely anchored, the stars continue to shine their ancient light across the void, the space between stretches quietly onward. You do not need to hold the weight of all these dimensions at once. You only need to remember that you are an intrinsic piece of the architecture, that you belong to the cosmos, and that the cosmos beautifully belongs to you. Take one final, slow, gentle breath. Let your body rest comfortably against your pillow, and let the vastness of the cosmic night carry you smoothly away into a deep and peaceful sleep.